I can start. Dear colleagues, dear friends, good morning. And first of all, I want to thank organizers for invitation to this very nice conference. So I will talk about spintronic emitters. We have this plenary talk that actually introduce many things regarding terahertz radiation, terahertz emitters, and this mega science setups. But also you can work with terahertz using normal tabletop setup, and we work with tabletop setup. So this is outline of my talk, some introduction. Then I will speak about spintronic emitters. Then actually the main part of my talk is polarization rotation intrinsically by terahertz sources. Spintronic emitters allows to do that. Then actually it will be introduction and some other people and also our old results, and the last part will be our new results. Spintronic emitters and their advantages. Normally spintronic emitter should have ferromagnetic material, thin film, but also it's metal ferromagnetic. And also it is necessary to have a high intensity, to have material with the high spin orbit interaction, and this is normally non-magnetic materials. And then you illuminate it by femtosecond laser. The shorter the pulse, the better. I will show afterwards why. And then you have terahertz pulse, which is also very short, almost single period terahertz pulse. What is the main advantage of terahertz emitters? That they have a very wide spectrum. I know that now there are research in area of other terahertz emitters, and they also shows that band gap, the bandwidth can be increased. But what you can get directly, and it's already in commercial spintronic emitters, this is up to 30 terahertz. It is important to have which material you use as a non-magnetic, and the best is, this one, platinum. Other materials also give some radiation, but the best is platinum. And also, instead of 2 layers, you can use 3-layer emitters, and also in this way you can increase efficiency. This is, can I see? No. Important thing that the total thickness should be not more than 6 or 7 nanometers, so you have to be able to produce very thin, very high quality metal films. So the advantage is spectral width. Let's see where we are with the spintronic emitters if you compare with the other emitters. So the highest power you can get from effect of optical rectification in non-linear optical crystals. Rectification I put in кавычки, забыла. No, brackets is скобки. And if you use this kind of commercial crystals that normally are fabricated by Terahertz, Swiss Terahertz company, then you can get conversion of 2-3%. It is the highest conversion efficiency. And if you calculate it in electric field in the maximum of the pulse, then you can get 85 megavolts per centimeter. This I just took from their internet page. In our measurements, we work with one much smaller, 1 megavolt per centimeter, that we can get from this spintronic emitter. So spintronic emitters gets really much lower. Additionally to organic crystal, non-organic, non-linear crystals are also used for ups. For instance, zinc tellure is very popular crystal, and this you see conversion is 3 thousandths of percent. Another typical emitter is photoconductive antenna. They also develop very fast, and I think that we have the talk today about also photoconductive antenna. Conversion efficiency is 10 here, if you see, 10 minus 4. And this is also I took just from the company Betop. But the spectrum is much less wide, but narrow, although people report that they can make some specific antennas that can also increase efficiency and increase the width of the band. So spintronic emitter efficiency is comparable with zinc tellure emitter. And there are another advantage, that polarization of terahertz pulse is always perpendicular to magnetization. So if you can rotate magnetization, then you can rotate polarization. Very easy way to do that. So this is also advantage. You can intrinsically in emitter perform polarization control. What for we need terahertz emitter with intrinsic polarization control? Here I present 3 types of polarizers. One is wire grid polarizer, then just quartz half-wave plate, and also this is here the structure as a corner reflector rotator. It is somehow similar in some way for retroreflector. Here you have big attenuation. Here you cannot work for frequencies more than 2.5 terahertz. And here it's really very, very inconvenient to align. We work with this polarizer in one of the mega science setup. So if we speak about rotator, which is based on spintronic emitter, then we can say that it operates in very wide spectral range, and it has no attenuation. Spintronic emitters are already commercially available. This is the company that produces that. And here, what they show on their web page. Left, you have a magnetic field or red circle here, and blue here means that there are two different direction of magnetic field. So then you have pulse that have opposite phase. So when you have maximum, now you have minimum. And they also offer polarizer, emitter polarizer with rotation. So here, on the left-hand side, you can rotate it just by hand, and also you can buy it with rotating by the step motor. But you have to rotate. You have mechanical operation, and of course, this is not so much convenient. And what is important with spintronic emitters, that you may change, that we invent, it's really our invention, that you can rotate polarization only changing the current that is applied for magnets, so only changing value of magnetic field, or magnitude of magnetic field. Here I will not even talk too much. Here is the reference. You can find there many types of polarization tunable spintronic emitters. They not only rotate polarization, they also make elliptical and circular polarization, but all mechanically. So now let's speak about mechanism of emission. So you put your pump on the sample, then you have the light is absorbed by ferromagnetic layer, and then you have electron that moves within ferromagnetic layer, and then this is the spin division, spin up and spin down, then goes different direction in non-magnetic material. And this is actually how it works. And then you have spin current converts to charge current, and this charge current, just by electromagnetic laws, it results in short terahertz pulse. If you speak more close, then you may have two mechanisms. One is optically driven ultra-fast demagnetization, and here electric field of terahertz field will be proportional to first derivative of magnetization. And another mechanism is terahertz spin transport. Here you have conversion from spin current to charge current by inverse spin Hall effect. What is important? That electric dipole radiation that is left by demagnetization, this is electric dipole that is right, generally much stronger, actually 3 orders of magnitude, than magnetic dipole interaction that is left, the demagnetization. So if you can compare, because it's really important to know which mechanism you have in your emitters. So if you can compare by value, then if you have inverse spin Hall effect, it will have much higher intensity. And what is important also, this is for all, like I said already, polarization of linearly polarized terahertz field is always perpendicular to magnetization. How to distinguish experimentally? Because if you have just one single emitter, if it's not possible to compare and with absolutely equal conditions, then it's another way to compare. You have to illuminate your emitter from front side. Front side means that you illuminate not from substrate. And another wave, backside, you eliminate from substrate. And then you have changing of the phase. If you have changing of the phase, because spin current goes opposite direction, then it means that you have spin Hall effect. Also, I don't mention before, but also for very few materials, special materials, it would be my last, on my last page, also can happen Rashbe-Edelstein effect, also you have the same behavior. But if you do not have change of the phase, it means that you have demagnetization effect as a mechanism. So, which are achievements? So first we made, what is very important from the very beginning, in order to rotate by just value of magnetic field, you need the sample which has in-plane magnetic anisotropy. Mostly people work with materials with out-of-plane magnetic anisotropy. But then you can, because everything happens in plane, you will not operate polarization. So specifically, we made, our colleagues made, by preparation, the sample in magnetic field just within the spatter machine, then you can get this in-plane isotropy, actually whatever you have, depending on magnetic field. And then here you can see the just magnetization, normal magnetization loop. So you have red, it is easy axis, and black is hard axis. It's not exactly, there is, we can, it's very difficult to get really coincident back and forth behavior, but it's very close, it's almost good. But the structure was terbi cobalt ferrum cobalt. This was made in France in collaboration with this group of Pernod. And their task was, because also you have, you also need magnetostriction for some effects. So I will tell later for what, but they were focused on this. And this terbi cobalt ferrum cobalt has very high magnetostriction, although for terahertz emitters, just which is controlled by magnetic field, it's not necessary. So, so what we have, this is if you get radiation when magnetic field directed along easy axis. This is the spectrum, and the most important, if its magnetic field is along hard axis, then you have black, this is and left scale, then you have angle of polarization rotation. So within specific magnetic field, which is actually an isotropy field, you can rotate continuously by just value of magnetic field. And what is important, that amplitude green stays the same, so it's a real rotator. Then, this is why restriction is important. We also made that French people, they made the sample that is multiferroic, so this is magnetic structure on top of piezoelectric. We also get polarization rotation, but only within 120 degrees. But also this means that we can rotate polarization in these structures by magnetic field and by electric field as well. And now for new results. So we decided what we need. We need higher intensity. So we just take the most efficient material, that is cobalt platinum, and also grew the films within when magnetic field is applied during fabrication. This was made in Nizhny Novgorod by a group of Sapozhnikov. So what we get? We get quite nice signal. We check that is inverse spin Hall effect. And the most important, oh, wait. And the most important figure is this one. So what we can see here, this is terahertz pulse energy in nanojoule per centimeter square as a function of fluence. Cobalt platinum, our experiment. So we have a specific range of fluence where intensity of terahertz pulse increases linearly. And after that, we have actually damage of the sample. It becomes not reproducible. I don't know why it's linear, but my guys put it like linear. It could be everything, but well, it's like that. But the working distance is between 1 and 4 millijoule per square centimeter. Okay, so, and this is, you see, this is what is the best reported. This is the star. So actually we have almost, not 10, but almost increase. So this is really the record. And the last part, I will say that because there are many people who work with transition metal decalcogenides. So we, and this is the idea of the paper that is on top in 19, that it should increase because semiconductor and single layer semiconductor works like a filter for hot electrons. And then really they obtain here, they have increase of 40 times or something like that. We also made it, but with flakes, and it was, we didn't compare which, we have the same intensity that's from terbium-cobalt and ferrocobalt structure, so they're actually very low. Then we also put we use not flakes, but CVD single layer, and we obtained, we cannot compare actually because we have 0, and then we have a nice signal. What is important, we also found out that is Rashba mechanism. And now this is a conclusion that I already discussed, and then I want to present my group. This is all my group. Dr. Arseniy Burikov actually is the main person in this area. We couldn't do anything without Professor Vladimir Preobrazhensky, who is theoretician, and without Maxim Sapochnikov, who prepared samples for us. Thank you very much. 22 секунды.
Really, it's fine. But one question remains. You told about the commercial spintronic devices. How do they rotate the the polarization?
No, they put their emitter just into motor, and that's it.
So your way is better,
of course. No doubts.
Thank you, speaker, once again. The next speaker, Professor Shkurinov.
Последний штрих компьютерной грамотности. Сейчас. Процесс преобразования маповского формата в формат вывода. Ну да, это проектил, видите. Сейчас, секунду, я не задумал. Ну, участники, 4 пропавших билета. Вот.
Лучше поэт расскажите доклад.
Да, да. Вот.
Вся интрига уже была.
Ну да, так как у нас сейчас такой сложный период, вы знаете, перехода в Курчатский институт, да? Но в отличие от вас, нас уже как бы вот туда интегрировали, да? И вот в пятницу уже должен быть окончательное решение новой структуры, да? Поэтому там вчера был такой маленький, такой сумасшедший дом, документы, которые надо делать там еще. Поэтому я уже, честно говоря, не очень верил, что вообще все попадут, да? Но вроде как решили вопрос. Да? Ну, вас это ждет, здорово.
В пятницу выступаем тоже, так же, как и вы.
Вот. Но мы остаемся просто филиалом. Да, мы всех участников института. Мы остаемся филиалом, но у вас, наверное, там по-другому все. Так, коллеги, ну это ладно, это наши такие вот интимные организационные дела. Значит, ну и что я хотел рассказать? Микрофон, а вот это, да?
Либо вот, если хочешь, скажу,
Да. Так, мы по-русски или по-английски, да? По-японски, да? Да, значит, вот такое вот название. Okay. The title of the lecture is Laser-like Terahertz Simulated Emission in the Solid-State Molecular Crystals. I will discuss. Okay, laser-like. It's more proposal, but nevertheless, I will speak about that. The preliminary results, which I will discuss, were published in this paper, Perspective of Terahertz Application of Molecular Crystals, and it's a review paper, quite recently published, and motivation of this work was done by Professor Kaminsky from Institute of Crystallography, Russian Academy of Science, and he discovered, I may say discovered, absolutely unique molecular crystals, which in comparison with existing other materials has very high breakdown, optical breakdown, very interesting nonlinear optical properties. So, and mainly I will discuss our result, which are made on this unique crystal. Okay, just we know well the scheme of how to obtain terahertz radiation, which it exists in two forms: it's narrow band and broadband. Broadband is what we name time domain technique. Time domain technique. Okay. А здесь этой указки нет, да? Она невидима. Окей. It's quite typical results which are already published by other group. We know we see the pulse terahertz radiation. It's an example of lithium niobate crystal. You see the quite broadband. And the typical range is between 0 and 2.5 terahertz. And usually the limitation of the generation is quite simple because it's phonon lines. And if we look the generation spectra on broadband view, we see that there are several phonon lines close to 5.3 terahertz for zinc telluride crystal, and there is frequency velocity mismatch for higher frequency. So it's two obstacles which I usually we have to avoid. So it's for non-lines, it's limitation for low frequencies, and phase mismatch for high frequencies. And normally this we cannot avoid for non-line absorption. We cannot avoid normally, and moreover, phase matching conditions not always could be achieved. Just for few words, what does it mean for non in solid state? It's oscillations of solid state atoms which are connected into into regular chains, and normally this for non-lines is dissipative mechanisms absorption, and usually it cannot eliminate the radiation in the normal way, if we take into account phenomenological approach, which, okay, we have to, usually if we have polarization, we may use Chi2 for anisotropic materials and Chi3 for isotropic media, such like in gases. We may generate Terahertz field, and then in the case of some phase matching conditions, we may have good conversion into visible to Terahertz radiation. It's typical phase matching conditions for Terahertz field, as we see. And you may see it's presented here in the case of no losses in the material. No losses. You see there are phase matching condition here. Chi3 it's material parameters, and but the general conditions are no losses here. And in the case of losses, for instance, like if we have phonon like absorption. Usually we have simply absorption and limitation of the generation bandwidth. These are simple calculations of phase matching conditions in the case of no absorption here and some absorption parameters. We will see it's very absorption influence on the phase matching conditions very efficiently. And normally we may have two type crystalline materials which delivers non-zero Chi2 accessibility. First, it's inorganic crystals, it's ionic crystals, which we know well, zinc telluride, gallium phosphate crystals, and some other. And another type of materials is molecular crystals. In comparison with ionic crystal, these materials consist of molecules which are aligned into the chains, and it formates regular structures in the crystalline form. Of course, these materials are quite known already. For instance, dust crystal. Dust crystals, it's already it's used many groups here, but from the point of view of practical applications, this crystal is not very much convenient, very much convenient because of hygroscopic properties and loss breakdown threshold. And of course, there are many attempts to develop molecular crystals because expected properties of such crystals are very high nonlinearities. And additionally to them, if we may apply the molecular design approach, we may change the properties of the crystal on our needs. So it's from the point of view of on request production of such crystals, it's quite perspective and ideas of widely use these crystals quite quite popular. But the problem is only there are two problems for such crystals. First, production of this crystal, and the optical properties of this material is not very much convenient for real applications. And what? The material we used, it's crystal which is assigned to the organic materials, which is developed by Kamensky. You may see that it's very transparent in visible range, in near infrared also, and it has quite a high nonlinear optical parameters. The property of the crystals is quite interesting, and you may see that it's transparent from ultraviolet to 1.5 microns, and also between 2 microns. It's transparent. It could be used different lasers for generation, and you may see there is absorption, Fanon absorption, original absorption near 1.5 terahertz. There are Raman active modes. The Raman active modes near 1 terahertz, and generation is assigned to this range, which is closer to Raman bands. And in this crystal, we may achieve simultaneous conditions, which is absorption. So it's here is infrared active mode, and also Raman mode, and in this case, generation is usually closer to Raman bands, and depending on the orientation of the crystal, we may have generation near 1 terahertz and for higher frequencies. I will show in the next slides. And what we may see here, there are two options for generation of radiation. First, it's electronic contribution of Chi2 into the polarization, and also resonance contribution, which is assigned to the Fanon resonance. And the value is resonant to electronic is high enough. So there is enhancement of the signal, because of the Raman and enhanced Fanon resonance. And of course, if we change the temperature, the generation bandwidth and the central frequency also changes. You may see that from 1.5 to 1.6 terahertz, but at the same time we may observe not critical generation, because if we change the wavelength, of the excitation, for instance, from 800 nanometers up to 1.3, the generation of the terahertz radiation then change properties, and it's also fixed on the Fanon line wavelength. If we change orientation of the crystal, of course, we change also generation wavelengths for different orientations. We have different ranges of the generation from 1 terahertz up to 1.5 terahertz. So this range could be completely covered if we change the temperature and orientation of the crystal. The origin is of this phenomena, which has not critical property, is quite simple, because if we address to the oscillation theory, simple oscillation theory, and if we have own native resonance of the oscillation Fanon oscillation system, and we excite it with very short pulse, of course oscillation will be done on the own frequency of the system, independently on the wavelength of the excitation. So this one is generation frequency, and it is short pulse excitation. In fact, it's not only one crystal. What I say in the beginning, that molecular design on request, was what we say on request, could help to have different crystals with different parameters, and of course parameters, it means that the wavelength of generation, of the intensity of generation. Here I show you Biftolat crystals, which we also produce, and we first developed this on request, because first it was calculated by molecular simulation, and then it was developed the growth process, and it also has very good optical properties. You may see the many generation wavelengths could be achieved here, and normally approach is what's quite mysterious for us. If we need wavelengths on request, so we need for some applications wavelengths of the generation, we may calculate the structure of the crystal, then develop the growth of the crystal, and then to have it in the experiment. And okay, maybe I will skip this one. For optical experiment, important for Goop crystal, for Goop crystals, for instance, and the same for Biftolat, and for, by the way, one of the good crystal for application is simply sugar. But okay, but for Goop crystal you may see that it optical threshold for the breakdown is highest for the all known to us molecular crystals. You see it's very close to lithium niobate crystal. In addition to that, of course, if we change some molecular groups of the crystal, we may change also the wavelength of generation the terahertz radiation. And you will see it's for instance, it's 6 crystals which we developed for sensoric applications. You will see normally they covered the range between between 1 and 2 terahertz. And of course, if we change the orientation and the temperature of the crystal, will also very slow change the wavelength of the generation of this crystalline, in these crystalline materials. And our idea and motivation of this experiment was, okay, quite, the Serse is coming again after some delay. And the idea was quite simple, that so it's okay, when we decided to study the S1 protein, we developed metamaterial like sensor, and idea was quite simple, that if we change protein, or if we change the material on the film, we should change also the localization of the field in such material. How we did it? We developed the metamaterials-based sensor with phase change material. So we use the laser to hit little bit material, and then we align the material into the enzyme we study in our experiments. But the problem is quite simple, because nevertheless all the curves of localizations are quite wide nevertheless. We change, but nevertheless quite wide. Localization is not so high. And you may see, but it's for phase change materials. But in these experiments, we thought that the best way, nevertheless, not to change transmission of the metamaterial, but to change the source wavelength of the laser of the terahertz source, to align it as much as possible closer to the absorption band of the enzyme. And so what we plan next step, to use molecular crystalline source together with metamaterials in order to achieve as high as possible selectivity of the sensors, because of the good alignment into the absorption bands of the protein. But nevertheless, combination of the phase change materials and the tuning source of the terahertz radiation is good way for the sensoric application in terahertz frequency range. Thank you very much for your attention. Okay, so you see it's a group of crystallographic. Now we have in FNIS crystallography of photonics, there is a group of gross materials. Да.
Could you possibly show the slide with the table of the parameters of your crystals? This slide.
Yeah.
The damping time of GAM and MAP crystals seems to be nanosecond. Could you possibly comment such very long damping time?
Yes, it's what I skipped, you see, because, okay, 20 minutes is not enough to to discuss, because what I taught in the beginning that it's laser-like emission. Laser-like, what does it mean, laser-like? In fact, it's not laser, it's more maser-like emission, yes? Because when we excite phonon system, this phonon is quite good, has quite good quality of oscillations. It means that what I told. So if the system is oscillating and the quality damping is not so high, it will oscillate for a long time after the pulse excitation. And in this table, as we may see, you may see these oscillations after the excitation. The femtosecond pulse is over here, and then there are some oscillations of phonon subsystems. This one, what you see, that it's translation of the oscillations from one orientation to another one, but nevertheless it's quite long. You may see it's close to 250 picoseconds. For the spectral studies, it's quite good, because if we have very long oscillations, quite high quality oscillations of phonon subsystem, we should have normally very narrow bandwidth. For spectral applications, very good. For sensoric applications, very good. For time resolved, of course not. Of course not. And in the beginning, we thought that we are losing one of the property time domain spectroscopy on this way. But then we saw that there is such technique we named like window transfer, Fourier transfer techniques. And we may use the window, temporal window, and then in this window we may get the Fourier transfer, and in this case, in particular in this window, we may study the spectral properties. That what we can do, we can change the position of this window, and then on this way to study dynamics of spectral components. So it means that some mathematical, very simple mathematical procedure may help to survive time domain algorithm nevertheless.
I'm sorry for the question, but I didn't understand. Why other crystals, not molecular crystals, do not demonstrate the same effects?
Okay, probably I was not clear. In fact, the property of the crystals we use has three critical points. First, it should be phase matched. Another, in this particular spectral point, it's phase matching, phonon emission, and at the same time infrared absorption.
All this lithium ion 7 terahertz and all these effects?
In lithium niobate, there are publications which demonstrate narrow band absorption. But nevertheless, in niobate, we have to use a tilted front to achieve phase matching. In this configuration, it was demonstrated that narrow band is possible. And moreover, if we change the angle of tilting, we change the frequency.
So phase matching.
Yes. Ну, то есть основной смысл такой, что совершенно случайно есть класс кристаллов, в которого вот эти три точки совпадают. Три точки совпадают, так.
То есть молекулярный ни при чем?
Во-первых, большая линия есть. Во-вторых, понимаете, в чем дело? Какая здесь, что очень важно? Вот мы заранее можем посчитать вот эти свойства, так, и сделать кристалл под эти свойства. То есть вот это вот в ионный кристалл практически невозможно, потому что или они растут, или не растут. Так. Вот здесь вот что мы можем, допустим, вот этот губт кристалл, у него есть водородная связь, значит, у него есть какое-то поглощение, да? Какое-то поглощение есть. Что можно сделать? Можно взять, убрать группы с водородными связями и изменить поглощение. Так? Значит, у него более широкополосно будет пропускание. Так? И при этом резонанс и нелинейность тоже возрастает в тех областях, в которых появляется. Да, как всегда, да. И поэтому у них преимущество вот это вот то, что называется по заказу, дизайн по заказу. Ну и хорошо, что есть группа Волошина, которая все-таки еще культуру Каменского сохранила у себя.
Там в пейсмейчинг тоже есть, это рамановское растение, смотрите, на неоформах рамовских, да, под нулевыми углами. Есть такие кристаллы, да.
Да. Ну да. Вот. А здесь просто, понимаете, все мы стартовали от вот этого приложения. Нам нужен источник был для сенсора. Так. Он должен быть простой, удобный, и хорошо перестраиваемый. Так. Вот. Это значит, что вот видите, вот мы там вот 6 классов сделали кристаллов, они перекрывают весь диапазон от 1 до 2 очень плавно. Так. Вот. Ну и, соответственно, и есть еще один момент, о котором мы не говорим, о том, что, например, даст кристалл в России невозможно больше растить, к сожалению. Почему? Потому что прекурсоры все под санкциями. Вот. Там есть еще такие вот нюансы. Вот. Но, с другой стороны, вот я приглашаю к сотрудничеству, там какие-то, может, что-то интересное на этих материалах можно получить. Все, спасибо.
Мы выполнили свою программу. Спасибо. Под моим мудрым руководством мы прогуляли кофе-брейк. Спасибо.
I spent hours trying to remember. Can't remember. The dream just seems too distant. I wake up to the sight of neon lights flashing outside my window. It's 5 a.m. I still can't get you off my mind. Distant sounds fill my head. I spent days walking the streets trying to find you, watching the people around me. Have I seen her before? Anything I've seen, if I could just recall. Is it just a dream? Have I seen her before? If I could just recall. Distant sounds fill my head. I spent days walking the streets trying to find you, watching the people around me. You're not there. Have I seen her before? Anything I've seen, if I could just recall. Is it just a dream? before. Anything I've seen. If I could just recall, is it just a dream? Have I seen her before? Anything I've seen. If I could just recall, is it just a dream? I keep having these strange dreams. I'm holding your hand, just as I'm about to tell you how I feel. The dream suddenly ends. Anything I've seen. Is it just a dream? Anything I've seen. Is it just a dream? Get the glory. Get the glory. Get the glory. Get the glory.
Get the glory. Get the glory. Get the glory.
прошу прощения. Вот. Dear colleagues, thank you for introduction, for good kind words. I will train my English after some break. Okay, so good training for me. So this report is some little review about some works that I was done with my colleagues in field of heritage science. It is a new field for me because earlier I was in biomedical optics, but I realized that I can use all the approaches and methods from biomedical and to the heritage science. Heritage science is a beautiful field of investigation paintings, working with museums, and it was interesting that this was mega grant, and the first leading science was Michel Mignoux, leading science that was working in Louvre. And nowadays it is the Moscow colleagues from crystallography, Elena Terещенко. So I will introduce some techniques that is will be comfortable to work with heritage science. First of all, it is different kinds of sources and detectors in terahertz fields, and on the left it is sources, you know very good, all of them, of course, and examples of detectors, and the radiation can be continuous waves, that is, can be modulated waves, and pulse duration. And in this variation, this variety of these detectors and sources, we should chosen some that is comfortable to work with heritage science. What it can be, we chosen with our colleagues from Bordeaux University. They built this table from Jean-Paul Guillet. It is a comparison of some of them. So first of all, it is continuous waves, and for example, it is CV raster scan, and we know that it is the sources is GaN diode and the detectors is Schottky. Also pyroelectric detectors, bolometers, and they work at different wavelengths. And then we have the resolution 1 to 2 millimeter on the object. It is minimum size recommended for object is 5 centimeter per square, and maximum size 300 centimeter per square. Then it is continuous waves and quantum cascade laser, that is multipliers and quantum cascade diode, also bolometer camera as a detector, and the resolution is few hundred of micrometers, and the minimum size and maximum size is 5 to 20 centimeter per square. And what I will talk today is the pulse and frequency modulated CV. So first of all, you know very good is conductive antenna, time domain imaging, and it is recommended size of the object is 2 millimeters to 100 centimeter. But I hope you see this column. It is a frequency modulated continuous wave, and it is working different kind nowadays. It's good that we have big market nowadays. So here represented 300 gigahertz, and it is a multipliers and heterodyne detection. The resolution is bigger comparative to another 2 to 3 millimeter comparative to pulse or quantum cascade laser, but it is very big advantages. So we can observe big painting, for example, in museum, and it is very miniaturized, it's integrated, and we can use that this mobile technique. So it is some representation of chirped waveform. So if we have frequency modulated CV, then we have different chirps, a chirp of modulated signal, and their B is the frequency bandwidth, and we have the chirp rate and period. It is the duration between these the neighboring pulses. So their bandwidth of frequency will be from F1 to F second, and this will give us the resolution of sampling, not in object, but in sampling. Very good resolution. One of the techniques is continuous scaling of silicon based on chip transistors, and investigations into 3 to 5 technologies such as inter-pair based transistor push up the operating frequency of electronic devices toward terahertz regime. And we use here the antenna, it is transceiver and receiver, and in one point, so it is modern static FM CV. And how to detect the distance to the object from the source and receiver to the object? It determined by the difference of the receiver and the reference signal and reflected signal. So solid curve is reflected reference, and dotted is reflected, and you can see the difference is delta, and I don't see it from his. So delta is the difference of time, and FB is determines the distance to the object. So distance is the equation of determined from the delta t, speed of light, refractive index, and we can achieve very good sampling resolution. You see, it is speed of light 2, and reflection, and B, it is a bandwidth. So it is. It can be very. It is very small. And the lateral resolution given by beam waist diameter is omega 0. For Gaussian beam profile is given by this equation. It depends on the numerical aperture. So for investigation the painting, of course the spatial resolution is big, but the spacing, sampling, по-русски самплирование, sampling will be very good result, and I will show you the results. So in this presentation, I give you some sample of scene view, then low-cost silicon radar, then pentametrics, terapulse, in 5 minutes. Okay. So first, this work was beginning in Bordeaux University named IMS Laboratory with group of Patrick Manet, Jean-Paul Guillet, Quentin Cassar, and we published some joint papers. They implemented experimental ski, and we in Etmo University realized the programming the interface. Um, this video, if it works, I don't know, will show us. Можно видео включить, извините? So you can see it is my painting. I took that from St. Petersburg, prepared, and here it works now in transmission regime. So you can see the source and detector on the both sides of the painting. But it can also work in a reflection regime because the source of this front side also works as a receiver, so it's TX or X. Here the frequency is from 75 to 110 gigahertz, so we can easily calculate the B parameter, and from 220 to 330 gigahertz. So the spatial resolution is 3 millimeter. It's very big spatial resolution, but for if you have I don't know what Ivazovsky 3 to 3 meters square, so it will be good resolution. And very good dynamic range. It is 50 to 60 decibel in English, I don't know. This is the scheme, how the optical, it uses mirror and HDPI lenses. So the 3-5 technologies uses sources, detectors, and optical signals at one single chip. What is the main advantages of this technology is the possibility to develop high frequency, high power, and low noise devices. And French colleagues achieved these results on their private collection of this painting. It is the transmission scheme, and we see the back side of the painting. And here the reflection in 100 gigahertz and 300 gigahertz. So very good inside the object. Also I achieved some results on my object that I prepared, and it is a pseudo-colored, and I discovered my letter T that was closed underlying layers, and also the scotch on the back side of the painting. Then silicon radar. This experimental setup was delivered for first in Bordeaux. Nowadays it's under construction at Mo University. And it is 120 gigahertz radar and transceiver based on silicon germanium technology. Is developed by Silicon Radar, Germany, as seen view, also Germany. And the great strength of silicon-based technologies is characterized by miniaturization. So the size of this plate is 1 centimeter square, and high measurement resolution and low cost. Why very high resolution, measurement resolution? Because it is 120 gigahertz average frequency, but the interval is 119 to 126 gigahertz, and we can easily calculate the B parameter is 7 gigahertz, so the sampling resolution will be very, very good. And this diagram showed us the angle of receiver and source works. It is only 47 degrees, the angular. So it is Arduino gantry scanning system. Its cost very low. In Russian, I paid maybe 100,000 rubles. And we bought only the German silicon radar. So we construct in it more the interface that help us to work with the object. The object was this women the face. And you can see it is the images achieved in reflection regime. This is from different layers. This is layer 12, 13, 14, 15. And you can see that the layers we achieved was 200, and the intensity of each layers was decreased. The most better results was achieved at 11, 15 layers. And then we, in Atmo, applied integration of the layers, and integration method is based on the integration method for selected set of layers. It uses the idea of structure of different areas of image, so it is okay. So it helps us to research some defects in different sampling layers. So I have no time for, I think I'm out of time, so I just 4 minutes. Okay, thank you. So some example, just this time domain Picometrics US. So the best commercial devices is, of course, USA. It is Picometrics. Nowadays it's Luna and TeraView. So nowadays it's not possible to buy this nice device, so we construct that imaging in Itmo University. So it will be homemade. But so our colleagues from Louvre, they are very active, and they in 2019 they make an adventure and one trip from Louvre to Великий Novgorod by this bus, this real French bus equipped with many different mobile equipment, as well as Picometrics. It's a real story. Difficult to imagine now. And you can see it is Sophia Cathedral, Великий Novgorod, Picometrics, and it is the icon, and they received an image and also the B-scan of the icon. Then we prepared a test object in Russian museum. It was some piece, a copy of Ayvazovsky, and on another side of the painting, the restorers put another painting. So it is very complicated object, consists of different layers. And on the back side of this painting was these strips of coloring, and we didn't achieve anything using just common optics. So in ultraviolet we see only the upper thin layer. Then in infrared we can go deeper and see some sketches that restorers put on the canvas. And in X-ray we can achieve everything because, of course, you know why. And we see the texture of the canvas, we see the craquelure, everything, but we cannot achieve in which layer what's the resolution. And we conduct these experiments in United Kingdom, in TeraView. This is our samples, and we achieve different scan. So this is a reflection from the done with the painting. The best reflection is a very bright line on the below. And in pseudocolor, we can see that at different range of terahertz, we can achieve different image of this painting. So we can see by eyes only this head of man, and in terahertz we can see the firstly the scalp, so it is this. Then we can see the texture, the canvas of the painting, and after that, if we go deeper, we can see the strips. So you can see the form of the strips, and it is this. Sorry. So I go to conclusion maybe. Just second. So with the technological advances offered by silicon germanium-based systems, the integration of radar transceivers offers the affordable system to open application field for sub-millimeter electronics. And we showed the disadvantages of frequency modulated CV system compared to time domain imaging. And of course, thank you for your attention. Спасибо за внимание.
Спасибо. Any questions, comments to this very nice, very interesting lecture to us? Kirill,
Maybe I have a short comment. When you use Terahertz so-called time-of-flight tomography, when you analyze the train of pulse to achieve information from deeper and deeper layers, did you use some data processing, or you just plot a train of pulses?
No, without.
Because you
processing.
can improve the resolution considerably, I guess, is through some inverse filtering or deconvolution procedures. You didn't try this?
Didn't.
Okay, thank you.
Okay.
Maybe my small 1 cent. Here, because I'm just real time looking for what this group is doing, because it's really a very good developing team, and what Olga shown, in fact, it's special distribution of the electric function on the surface of the painting, but the electric function is quite difficult to interpret in terahertz, because it's some of them conductive. They have different region of the conductivity. Sometimes is ionic, sometimes is electronic, and so on. And this year, also the member of the group is Hadzinski, I believe. He published an interesting paper about modification of the model of the conductivity of Tolkien. Tolkien in 1957 suggested the model of the conductivity of thin films, conductive films, and Hadzinski just published a paper this year about how to modify this model, which is closer to reality of terahertz origin. So like modified model. Maybe you may cooperate with him just in order to reconstruct imaginary the electric function. In this case, it will be what's importance of that is you may have absolute data of your dielectric function from one painting to another one, if you operate with complex dielectric function, but not density like you have.
Okay.
You just comment. But the group is very interesting, in fact, and I think that we will see new results soon. Thank you. Any questions, comments? Okay. Thank you very much. Thank you. Okay, Nikolai Panov. Yeah. Thank you. Молодец. conical emission from DC biased filament and 10 terahertz. No, first of all, thank you for your coming. I know that it was not very easy for you, but it's already priority of terahertz community. So you have your time to tell us what you are doing.
1, 2, 3. I would like to thank the organizers for for the invitation and giving me possibility my results with you, giving me and I present the results of the investigations in Lomonosov Moscow State University and Lebedev Physical Institute in Moscow. Okay, a femtosecond filament is a source of terahertz radiation. It is a well-known fact, and but it is very low conversion, and the most of results is of fundamental physics, of the interaction between the laser and matter. But if one uses two-color femtosecond pulse, if one focus fundamental and second harmonics into gas, in air, for example, the intensity, the efficiency of the Terahertz yield increases by several orders of magnitude. And this effect of two-color filament, terahertz emission by two-color femtosecond filament has been studied in details. For example, not only experimentally, there are good theoretical models based on propagation equation. So it has been studied in details. Another way to increase the Terahertz yield, the efficiency of optics to Terahertz conversion, is to place a femtosecond filament between the electrode into the plane capacitor. So this allows to increase the Terahertz yield in the scheme by probably 1 or 2 orders of magnitude, and this effect was observed. What we know, not very lot. We know that the spectrum of Terahertz emission from DC biased filament is not very broad band, up to probably 3 or 4 terahertz. You can see here the results of the measurements. We know that the directional diagrams are on axis, something like bell-like directional diagrams. And that's all. We measured the spectrally resolved directional diagrams using this scheme and observed that they have probably not bell-like, probably flat top-like shape, but we observed on-axis emission both at different frequencies from 300 gigahertz probably to 1 terahertz, flat top directional diagrams. The results agrees with the previous works. But in theory, the theory is much more poor. It's only interference model, and interference model of terahertz emission from a filament are always correct. They represent the experimental results. They have a lot of parameters, so we can always reconcile the experimental and numerical theoretical results. And that's all from theory. So in this work, we use the propagation approach, self-consistent 3D plus time simulations, and we predicted the conical, not flat top, not bell-like emission from DC biased filament at high terahertz frequency of about 1000 of terahertz. And then we observed this effect. So my presentation is slightly boring. Predicted and observed. So let's talk about our prediction. We used the unidirectional pulse propagation equation, which is non-paraxial. We account for both for Kerr nonlinearity of bound electrons and the nonlinearity of electrons released during the acts of the ionization. This equation is non-paraxial. We did something to simulate the terahertz emission from DC biased filament, so we have to remove the DC field from the propagation equation first, and second we have to increase the resolution. There are a lot of efforts, but it's our theoretical simulations problems. We did, and I think the reasonably good agreement between the experimental and numerical results. You can see the agreement, and this is the results up to 1 terahertz, but what will be at higher terahertz range? And this is the frequency angle distribution. You can see the ring-like the directional diagrams at high terahertz range and in low frequency terahertz range. Flat top, but the ring at the frequency of about 10 terahertz or 20 terahertz. Conical emission. The origin of this effect is the superluminal motion of the ionization front, which emits the terahertz radiation. It moves slightly faster than the speed of light, and as a result, at high frequency THZ range, the terahertz wave interfere destructively, so as the ring-like structure appears. We calculated using the simplified approach this interference integral, and our estimation of the absolutely zero on the beam axis, absolutely zero terahertz signal on the beam axis is 20 terahertz in reasonable agreement with the results of numerical simulations. We observed the signal at 17 terahertz. One can calculate this integral in different ways. For example, we can use the Fresnel theory, Cornu spiral, very simple, very simple representation. In English, it is called the vibrational curve. So this integral is this Cornu spiral represents this integration, and the zone, the diameter of the zone of a Fresnel zone is the displacement, temporal displacement of the ionization from 0 to somewhere. This is the Fresnel zone in our simulation, in our model, and this is probably good analogically from diffraction theory to Terahertz emission theory. Okay, we predicted that at 10 terahertz we can observe a ring. So we predicted, so we have to observe. What do we need? First, we need 2D measurements. Because you can see that the measured before us spatial angular distributions of terahertz emission is strongly modulated. So we can lose our ring-like structure in 1D. One slice and we lose this something like here. This is this ring or is this modulated ring or is this bell-like distribution? We do not know. So we have 2D measurements. We did the device to measure two-dimensional angular distributions. It consists in horizontal plane, we rotated the bolometer, and in vertical plane, we moved the mirror and place a filament. We move a mirror along the vertical axis and push the laser beam between the electrodes. It's not probably excellent way to measure the angular distribution, but we have what we have. This is the first problem. And the second problem is to find the appropriate material to block the optical radiation. Because at 10 terahertz, Teflon usually used in the experiment is opaque, and we cannot. So we find the polypropylene plastic and used the 400 microns. 400 microns polypropylene film to block the optical radiation and to pass the terahertz emission from a filament. So I think this is all we need to measure 10 terahertz radiation from the DC biased femtosecond filament. And we measured. We used filters, band pass filters here from 500 gigahertz to terahertz filters, Tidex. And at 500 gigahertz, we see the typical distribution. This is bell-like, probably flat top on axis emission. At 1 terahertz, something like this. But at 3 terahertz, the first trace of conical emission appears. But you can say that this is not accurate, not accurately measured bell-like function, something wrong, non-ideal adjustment of optical elements, and so on. But at 10 terahertz, we see good ring-like structure. Of course, it is strongly modulated, but this is ring with minimum at the optical beam axis. So this is the ratio, this is the contrast of our ring, the ratio between the maximum signal and the signal on the beam axis. This ratio is about 0.5, and this is in reasonable agreement with our 3D plus time simulations, in which the ratio of 0.5 was at 8 terahertz. So the reasonable, I think not reasonable, good agreement. And the conclusions are slightly boring again. We predicted and we observed the conical emission at 10 terahertz, the conical emission from DC biased filament. And thanks a lot for your attention.
Thank you, very interesting. Questions, comments to very interesting lecture? Vasily.
What is the spectrum of radiation at 10 terahertz? Is it a noise generation or a sinus?
Spectrum at 10 terahertz. What do you mean? Around, this is not noise signal. Since this is a coherent signal, because we have the directionality of this signal. This is directed by a small angle along the beam axis. It's not noise. It's coherent signal, something like sinus. And in temporal, but I think in temporal coherence could be interpreted like as spectral coherence here, I think. But at 10 terahertz, it's not noise. In temporal domain, it has a fixed polarization along the DC field. So I think it's not noise due to these two facts. About spectrum, we didn't measure the spectrum, but classical spectral measurements cannot come to 10 terahertz. This is ABCD TDC detection. We cannot. They show noise, but in our experiment we use the bolometer. It's not noise.
Thank you for your talk. I have a question about your experiment. Why you use the cryogenic bolometer system for detecting your radiation? As I know, the sensitivity of this detector is not high. And why you use this detector?
I think the sensitivity is rather high, in fact. The parameters of our sensitivity are shown here. It allows to observe the terahertz signal at 10 terahertz. In fact, the Galilei cell cannot do that. We tried to do the Galilei cell. No. TDS, some TDS techniques are not suitable in our case because our laser has 10 Hertz repetition rate, and we do not work in our system. So we have only bolometer or Galilei cell, and I think the bolometer is better suitable for our talk, and we have the bolometer.
Thank you.
Okay. my question general. In the intro part of the okay. Thank you for your talk. My question is general. In the intro part of your talk, you say about the very low efficiency of terahertz radiation from single filament, and so the DC biased is one of the paradigm which give you the enhancement of this efficiency. Because you made a lot of theoretical predictions, a lot of numerical simulations, you can, I think, answer the question what you're expecting to the record values of the efficiency in such a concept. And maybe you can comment how it can be realized in experiment.
We did one simulation with Garnov group, with Booking group. They did the experiment, they mixed both second harmonic and the DC field. So in the case of the lowest, THZ yield from two-color filament, then the polarizations are perpendicular. That THZ yield from DC biased filament is the same. So we can speak that the efficiency of DC bias scheme is probably 10% or 5% or 1% of the two-color yield. Two-color yield provides the efficiency up to probably 1% in mid-infrared and 0.1% in using titanium sapphire.
Yeah, maybe some comment also. In fact, the maximum efficiency was achieved by Alexei Balakin when he measured generation in liquid nitrogen. And liquid nitrogen, there is an effect which is quite closer, a self-organized electric field because of the ambient diffusion effect. There is formation of the capacitor there, but the advantage of that capacitor is first it's synchronized in time with optical pulse. At the same time, the electric field is larger because it's pulsed. And efficiency was, I don't remember, but higher than it could be with a flat capacitor, which has first flat geometry, and another disadvantage is permanent field. But nevertheless, it's very interesting calculations. Maybe if you discuss with Alexei, you may use the data of experiment in liquid nitrogen and to compare it. But nevertheless, our observation was that efficiency is higher in liquid nitrogen.
We always try about polar diffusion, but it's very, very complicated effect.
But in gas, you should not take it.
In gas, of course, in liquids.
But in liquid nitrogen, we measure. Okay, in water it's impossible to measure, of course. But liquid nitrogen is sufficiently high. We expected that it was closer to maybe up to 20 kilovolt field there. Thank you. Okay, very, very good talk, and I'm really very grateful for your coming.
Thank you.
Okay. Okay, I would like to announce the next lecture of our session. Sergey Morozov, low equivalence emitters based on very complicated quantum wells, luminescence, stimulated emission, lasers.
Thank you very much for invitation. First of all, I would like to thank the organizers for possibility to deliver my talk at this very interesting conference. Okay. Today I will try to discuss our last results and maybe few history about very interesting, in our opinion, mercury telluride, cadmium telluride quantum well structure. And here you can see the teams from our Institute on for Physics of Microstructure, Russian Academy of Science from Nizhny Novgorod. And here, very important team from Novosibirsk, where all the structures were grown. We have some collaboration up to now with a university from Montpellier. And this is typical outline of my talk. Introduction, very short introduction about properties of the narrow quantum well structures and narrow band gap MCT alloys. And the main part, I will try to present the original results of photoluminescence and the laser emissions in such structures. And first of all, very short introduction, as it is well known, very well known, owing to the inverted band structure of mercury telluride, the band gap of MCT alloys can be tuned from 0 up to 1.6 electron volt. In fact, with cadmium telluride. Nowadays, mercury telluride, cadmium telluride quantum well structures as the bulk materials attract much attention since they exhibit a number of remarkable fundamental properties such as normal and inverted band structure, some topological and serrative properties. And few years, 10 years ago, it was a boom in this investigation, first of all, theoretical investigation of such structures. Typical two-dimensional semi-metal band gap in such structures with narrow band gap. And in our opinion, these structures are very promising for applications too, as promising materials for, of course, long wavelengths detectors, interband detectors, and in our opinions, the emissions in the spectral range from 30 to 60 micrometers. You can see here the picture of the emission for QCL points, and you can see in the mid-infrared range, this is a leader in this spectral range, typical operation time at close to room temperature. Some more problem in the Terahertz wave from 60 to 200 micrometers. Typical operating temperature not very high, but the last paper in 2020 in Nature Photonics shown that in 2022 that the beautiful results from the American group that we obtained the operating temperature for QCL in Terahertz wave close to 250. But in our opinion, we try to, and you can see here the problem for QCL lasers in the optical absorption in F3B5 materials. In the spectral range from 30 to 60 micrometers, QCL is not working because of phonon and optical phonon absorption F3B5 materials. In the same time, in the MCT, the optical absorption shifted compare F3B5 materials to long wavelength range from 60 to approximately 80 micrometers. So, in our main goal to manufacture some emissions sources in maybe lasers in the spectral range where quantum cascade lasers is not working. And few words about very interesting materials, lead salt diode lasers. You can see here the orange curve that up to now in semiconductor materials we already have results of lasers, but with some problem of operating time and the low operating power, close to moving this type of materials in the commercial application. Concerning MCT-based lasers, you can see here a few green points in the scheme, and the best results from the wavelengths was obtained in 1993, and 5.3 micrometers wavelengths in the MCT lasers was obtained. And let me present the original part. You can see here the experimental scheme where all the spectrum were measured. This is basically all the spectrum were measured with Fourier transform spectrometer operating in step scan mode. This is very important, step scan mode, very important for reducing room radiation background signal that is very huge in mid and especially far infrared range. So this is the typical picture from the books. Where they presented three basic mechanism recombination, interband recombination in the semiconductor. Two of them, this is non-radiative, Shockley-Reed Hall, left part, and the Auger recombination and the radiative recombination. And in our materials, the Shockley-Reed Hall recombination is not very, very important because our best guys from technological team to have a structure with a very low level of residual impurities and residual defects. And here the results which we obtained in 2014. And you can see in our first experiments of photoluminescence, we observed in bulk, important note, in bulk samples, MCT up to 25 micrometers wavelengths. I'm sorry. And in MCT quantum well structure up to 16. The next, we measured also the different structures, and up to now we have a photoluminescence up to 14 micrometers wavelengths at different temperatures. So the next step, we try to produce some resonators, some waveguides in such structures, and for laser emission, very important different three different properties: optical and structure quality, conditions of population inversion for stimulated emission, and waveguide. So before we presented waveguide structures, I will try to present the very important result of time result for the photoluminescence measurements in quantum well structures. You can see here the result of such experiments. And the main results of such time-result photoluminescence, we obtained the typical relaxation photoluminescence time, radiative time, around few microseconds. In the future, it was very important in population inversion. So in order to achieve the laser action, we designed few waveguide structures and calculated compound properties. Here you can see the results of such calculations for structure to interband transitions around 10 micrometers. And here, this is TM-mode localization, is rather well. In maximum of TM-mode localization, we placed few quantum well structures, and all the structures were grown gallium arsenide substrates. You can see here left part, and the buffer layer. And typical buffer layer was the thickness was around 10 micrometers. And you can see here in 2016 we obtained the result with stimulated emissions, not the photoluminescence, and quantum well structures up to 10, around 10, close to 10 micrometers. You can see here we jump and 2 times more that were obtained in the international team up to that time. So the main reason using quantum well structures, you can see here the typical calculation picture for energy momentum level for bulk and quantum well structure. A quite different energy momentum low for bulk and quantum well structure. You can see in the left part of the picture typical parabolical energy dispersion law for heavy hole and light hole. And you can see in quantum well, especially in quantum well, narrow quantum well structure, the energy momentum law is like hyperbolical, especially in close to k vector close to 0. Why is very important? Because in this, it is known, maybe not very well, that in a hyperbolical energy momentum law, with not close, with not zero band gap, the Auger recombination impossible or significantly suppressed. So our structures, quantum well structures, have like here, energy momentum law. That's why we have a very good situation with stimulated emission from fundamental point. Unfortunately, really structures, quantum well structures, MCT, not very, very hyperbolical, and you can see the side maximum, side line, and maybe sometimes this is a problem, because if the hole put here, the Auger combination will be start. So, in fact, really in our structures, the typical situation, this is for obtaining the result, the stimulated emission, laser generation, this is really competition of Auger recombination, non-radiative process, and radiative recombination. So, just a moment, okay. So, step by step, we calculated other integrals for other structures, waveguide structures, and here you can see 20 micrometer stimulated emission 2017. And finally, we try to calculate very interesting design where the T-mode localization, important node, was achieved due to Australian band of gallium arsenide substrate. In fact, the reflection index in spectral in the wavelength around 36 micrometers confinement due to Australian band of optical, in fact, optical phonon-sense gallium arsenide substrate. And in such structures, we obtained, what is it? Okay. This is problem is the presenter, no? I don't know. What is it? Okay. And few years ago, we obtained the result and stimulated emission around 30 micrometers, 31 in 2021. It was presented, it was published in ACA Photonics. And so up to now, we cover the spectral range from 10 to 31 micrometers with different temperatures in waveguide structures. So, and then maybe up to now, it's very important, the 31 micrometers, because this is first point in the close spectral range for quantum cascade lasers. So, very interesting that in such structures with varied the temperature, the stimulated emission was stability, not moved. It was very strange. Why? Because you can see here a picture of the calculation, the mode loss, optical mode losses in such structures, the gray dashed line. And you can see here our stimulated emission is the left part of the such line. So if we change the temperature, increase in the temperature, and the stimulated emission line disappears due to increasing mode optical losses in such structures. How to optimize with waveguide for obtaining the more long wave spectral range stimulated emission? This is a typical, very standard typical way to increasing the buffer layer and in dielectric waveguide. And in such structures, you can see here results of calculation for two structures with different cadmium telluride buffer layer, 10 and 15 micrometers, with mode optical losses. And you can see the optical losses drop significantly in 15 micrometers cadmium telluride buffer layer. In such structures, they obtain results the stimulated emissions, please, very important, known in watt, the threshold pumping in 1 watt per square centimeters. Compare not optimized structures, where 5 kilowatts per square centimeters. This is fantastic results, because it's more than 3 order drop in the threshold, in very perspective for application. I think this is maybe the best results in our group for 10 years. Why? Sometimes it's a problem to explain the results, bad results. And sometimes it's a problem to explain the very good results. I don't know why. Very simple application. Of course, you can see here the 1 order we have in decreasing of mode optical losses. Okay. What's the next? The next, you can see here, important, that we obtained the results. No, just in CV mode, so it's continuous wave mode. Compare pulse mode in 5 kilowatt per square centimeters. So if we have the competition in this case with T-pulse, time pulse of the optical pulse, and radiative recombination time. And maybe you remember that a few slides ago we mentioned that this is 5 microseconds. Okay, and in this case, when the optical pulse pumping were many low, significantly less than T radiative time, and if we have a CW mode, this is the situation quite different. Why? All the carriers in the CW mode using for population inversion. I have few minutes. Okay, this is not very interesting, and few pictures about real optical pulse laser generation. In now very popular commercial, yes. And you can see the results of the first results of the laser generation in resonator, Fabry-Renault resonator, based on such structure with etching due to ion beam. And you can see the dashed blue line with stimulated emission, and this is resonator mode generation. And after that, we produce some interesting microdisc, and also whispering mode we obtained in 330 Kelvin. And let me present very interesting. There is this result was obtained yesterday. This is picture from my phone, my mobile, and we obtained in microdisc the stimulated emission around 23 micrometers. It's very good because the most part of my presentation this is stimulated emission results. For real laser application, very important laser generation. So thank you very much for attention. This is the conclusion of my talk. And first of all, very important using this quantum engineering for suppression of Auger recombination in such narrow bandgap structure. Thank you.
Thank you, very interesting. Maybe just before the question, just comment. You may see that Sergey is also doing the artificial crystal, because multi-layer structure is artificial crystal, and also he is doing it on request, so he calculates the structure, and finally he has tuning narrow band radiation. We are doing the same by molecular crystal, but Sergey is doing by molecular beam epitaxy technology. It's just today's trend, different directions. What could be the winner, in fact, because nevertheless, narrow band radiation is now required in many applications, many applications. And so we are not competing, but the same you see also low frequencies, because it's also Fanon mechanism of enhancement. But my question is quite simple. Why you see that stimulated emission, but not lasing? In microdisc.
On microdisc?
Mm-hmm. You see it?
This is not a big problem, because you mean that in microdisc some of the problem how to output of the radiation, yes?
Yeah.
It's not problem because our meter is not very, very good. We have some defects in the round, and after, I don't know why this is a problem to have a stimulated emission. Maybe you mean the problem of the optical losses in such structures, yes?
No, you say that it's stimulated emission.
Yes.
But not lasing.
Okay.
It's two different things. Two different things.
Yes, yes. You're right. This is, you can see results yesterday. We have many results of a microdisk stimulated emission. Unfortunately, I'm not to present our results in such structures. And this is typical with stimulated emission with around 20-25 inverse centimeters. And this is the first picture where I have a mod. Of course, for better to explanation, I must to show the results of picture of stimulated emission in such structures for better compare with results. But if we to put of here, this is absolutely whispering mode in with such structures because now we try to publish in the appel. Because you can see the equidistant mode calculated of diameter of such microdisk. This is very good correlation of the theoretical calculation of whispering mode and the experimental. For this result, maybe not very good explanations to the moment, but I believe this is a real laser generation, but we will see, sure. This is a good question.
Gregson, am I right that I'm... it's lasing.
Yes, yes. I hope, because we maybe you can see, this is the spectral range around 4 micrometers wavelength. This is not very, very long wavelength. And this is the first results with very well obtained for laser generation because we measured a lot of different microdisks. And we now the technological of etching of such structures move it parallel in our experimental results because it's very, very difficult to etch in such structures because very, very soft materials and typical scheme, ion beam, chemical etching doesn't work in such materials because it's problem, extremely big problem. And our best guy, star guy of the etching, ion etching, to move it in this science parallel our group.
Yeah. So I'm sure that if you digitize the intensity of your generation peaks, you will observe saturation for sure. It's the first indication of the lasing. Okay.
Thank you for your talk. My question is about can you control the line widths of your generation, of your stimulated radiation? Because in practical applications, it's quite important to the line widths of your generation. For lasers, it's also very important.
Yeah.
When you just tune, when you just tune your wavelength by the temperature, you have a lot of effects, some kind of the maybe homogeneous broadening or inhomogeneous. You say nothing about this, but you work with the semiconductor materials, and so there some kind of problem with the crystal lattice non-homogeneities, and so what is about the line widths? How you can control it over the broad range of your spectrum?
You mean the laser generation or stimulated emission?
I mean both stimulated emission and lasing.
Okay, a good question. Sometimes this is a really problem because you can see here we use the optical pumping with different wavelengths, and with the absorption too big, of course the temperature of the structure, I mean the bulk temperature, the grating temperature, move it. But if we sometimes use the pumping into the quantum well, the absorption coefficient in bulk structure minimum, And of course, in such experiments, the stability perfect of the line. And you can see here we measured sometimes our results with extremely high resolution vertex Fourier tensor spectrometer. 0.2 inverse centimeters. It's different, maybe at a few hundreds of micro EV, maybe 0.1, 0.2, maybe.
Thank you.
Like here. Yeah.
Cool. Yeah. Thank you. But
this is very good question. For practical application, when we use the, for in the future, I hope, the current pumping, it was a big problem. But this is typical situation for interband laser, for semiconductor laser.
Yeah, thank you. Okay, it's important presentation because I remember many Sergei
You are currently the only
presentations,
person in this
and he
conference.
passed very long way from theoretical lasers to the practical one. What we see is that now it's real lasers and a real device. So my congratulations. It's
Thank you very much.
It's very good. Thank you. No questions anymore. It's just because of no time. So we have to shift our presentations. If effect of magnetic field, is it who will present the next effect of magnetic field and injection current on spectral characteristics of multiple quantum wave lasers? Okay, yeah. Okay, please introduce yourself.
Okay, thanks, Professor Rustam. First of all, I'm Professor Aurangzeb Khurram Hafiz from New Delhi, India. I actually work in several topics, and one of the topics that I had worked several years ago is what I would like to present, because I thought that this is a hardcore laser conference, so I should stick to that. First of all, I would like to thank the organizers for inviting me here. Special thanks to Professor Pavlyov, with whom I've interacted on several occasions. And that's one of the reasons why immediately I accepted the invitation to come to this place. The topic of the day is something which has been studied for over, I think, 4 decades. But it still interests us because there is always something new whenever we enter into this particular field. Before I go into my particular work, I would like to have some theoretical background. Of course, the earlier speakers have spoken a lot about quantum well and all, and I'm sure many of you are quite aware about the things, but for some, it's just an introduction that I would like to give. So the idea of multiple quantum well laser is very simple. You have a stacking of single quantum wells and you make a multiple quantum well laser. We have not made it. We have obtained it commercially available laser through Hitachi, and that's one of the reasons why it was on a particular wavelength that we had worked on this. Okay. The important aspect that I would like to share here is if I can manipulate the energy levels in the quantum wells, I can actually manipulate the radiative transitions and, of course, the lasing frequencies. Now, whenever we talk about magnetic fields, especially strong magnetic fields, it has been, I think, several decades that people have understood the evolution of Landau quantization that takes place whenever semiconducting material is exposed to high strong magnetic field, but the temperature aspect has to also be incorporated, and so we have to be in a temperature range of, let's say, less than 100 Kelvin, and in that case the emission properties of lasers will be guided by the strong magnetic field effect and also the polarization part. Of course, the quantization of interaction energy of the charge carriers and magnetic field leads to as I said, the emission properties. The wave functions, therefore, defined in this particular aspect is mostly of Gaussian nature. This is basically a theoretical aspect that says that the whole theory leading to the Landau levels can be approximated from harmonic oscillator problem. And the interesting part is that if the energy levels are continuous, then with the application of magnetic field, we can actually discretize it. Okay, so the aspect that I would like to speak about is, in the earlier days, it was seen that when we are exposed to strong magnetic field and in low temperature, that is around less than 100 Kelvin, the oscillation wavelength showed a blue shift with increase in the magnetic field. And of course, there was an increase in the threshold. Now, how this was explained during those days because of the Landau levels, that when we expose the magnetic field, the energy gap between the discrete electron energy level and discrete hole energy level increases. And therefore, we get this particular change in the oscillation wavelength. But when we talk about a room temperature case, which is a more practical example, wherever we talk about a room temperature case and a low magnetic field, then the dynamics became totally different. What it was observed that a red shift in the oscillating wavelength was observed, and it was also observed that the direction of magnetic field vis-a-vis the area vector of the active region played an important role in determining the kind of oscillation wavelength shift. So some of the reasons which people had given was that the not only the oscillation wavelength but optical output, your injection current, everything dependent on the was dependent on the magnetic field, and therefore the shift occurred because of the magnetic field variation. So what sort of mechanisms are involved in depth if we go in terms of the dynamics of electron hole recombination? So first and foremost, there is a change in the energy band structure, and if we have to put it like that, because of the Landau levels, we have one aspect, then the recombination dynamics, that plays a different aspect. So there is an interplay of the Landau splitting as well as your recombination dynamics. Of course, this affects the optical properties of the lasing setup, and one can actually have a control of the lasing wavelength or oscillating wavelength because of the interplay, or having a control over the interplay between the two systems. Okay, one more thing, that when we have a strong magnetic field, there is actually a separation in the cyclotron orbits of electron and holes. So this basically suppresses the recombination process or probability of recombination. Now coming back to our work, we did our work in aluminum gallium indium phosphide MQW laser. We had got that, acquired that chip from Hitachi, commercially available, and we had put that naked chip in our experimental setup and obtained the results. So these were some of the papers that we had done in the past. Okay, the highlight of our work was that we reported the effects of relatively weak magnetic field on the threshold properties on spectral characteristics of aluminum, gallium, indium phosphide laser. The threshold current and temperature characteristics increased while the output power decreased by applying the magnetic field at different directions with respect to the quantum well plane. The spectral shift mechanism is explored with a threshold current and characteristic temperature. The carrier density dependence conveyed that the redshift of the spectral emission is due to the band gap narrowing or band gap shrinkage. So our observation was that whatever the earlier theoretical background was given, our was a bit different from that, and our analysis was correct to that aspect. So this was one of the homemade setups that we had created in our labs, wherein we had stacked up everything in a small space. And this is the schematic that we have. And as you can see, that we had considered parallel, B parallel N and B perpendicular to N. Maximum changes was observed when we had B parallel N, and minimum changes when B perpendicular to N. So we can also see the change in the injection current in presence of magnetic field and in absence of magnetic field. Okay, so this is how our threshold condition changed with the magnetic fields and injection current and power output. This diagram which we had shown of the change in the spectrum of the laser output, primarily because of the effect of temperature, and there is always also the change in the full width at half maxima of the laser output. So our conclusion was that magnetic field had induced band gap shrinkage, which also is referred as Stark effect. And of course, it's a crucial mechanism in modifying the electronic structure and subsequently the properties of MQW lasers. The magnetic Stark effect is a consequence of the interaction between magnetic field and electrons' intrinsic magnetic spin moment and orbital motion. So when this particular field is applied, when magnetic field is applied to the quantum well structure, it exerts a force on the electrons and holes, leading to a change in the energy levels. But this was not all the case. So there were two aspects that we had discussed. One is the band gap shrinkage. The other was your recombination probability, that the two together had resulted in the changes that was observed. Okay, as I said that the magnetic field had resulted in band gap shrinkage, for which we had obtained the redshift. And as I mentioned, that there is a interplay of forces or interplay of between the band gap shrinkage and the recombination dynamics. Together we get that particular result that we had obtained. So in a nutshell, we had basically seen that the interplay of band gap shrinkage and recombination probability had resulted in redshift of the laser output, as well as your change in the output power and threshold conditions. The important thing is that still we are working on a theory that would actually connect different regimes: strong magnetic field, low temperature regime, and weak magnetic field, room temperature or high temperature regime. We are also working on a theory that would actually, instead of because this particular experiment was performed in a laser diode of oscillation wavelength around 660 nanometer. But we are now trying to move in to work instead of 660 nano in the terahertz regime. That particular part is still in the process. So we are still way off from the thing. Why this study is important is because we can have these particular applications in much more better and much more efficient form if we continue in this particular study. So my idea was this much, and I really thanks for your patience.
Thank you very much. Thank you. Very interesting. Very interesting. Yeah, first of all, I would like to welcome colleagues from India here, because we know that Terahertz community in India not very wide, but growing, very growing. And just a week before we was a conference in China, we discussed with international community that there is visible indication that its community is really growing in perspective. So you're welcome. Thank you. Welcome on board.
Thank you.
Thank you. Any questions? Any questions? Okay, Sergey. It's
I think
quantum wells. What number?
Whatever the specifications that we got, I think it was around 12. 12. That was the specifications that we had got from the company. So because we did not create on our own, so we had no particular clue of.
Because it's a difficult situation, because one way to be increasing efficiency is increasing quantum well. The next one, it's a problem with the losses.
Absolutely.
Calculation showing our structures, 5 quantum well is perfect. So this is a good for our spectral range. I don't know for you. 12 it's
12 it was, and I remember it.
okay, any more questions? I have just a general question. You use magnetic field.
Right.
Magnetic field, but maybe oscillating electric field will be more efficient. Because magnetic field is quite difficult to use.
Actually, the difficult part is not the magnetic field. The difficult part is to make that particular setup in which you can push that thing through the pole of the magnets. That is much more difficult, which we had. So we had designed a very small holder to place that in the uniform magnetic field. So that part is difficult. Otherwise, you are correct. It's easier to have with the electric field instead of magnetic field. So now we are planning to have that particular experiment performed on a terahertz regime, a terahertz source. So it is actually, we have obtained a terahertz source, which Professor Pavliev knows. So it's to work on that terahertz source in presence of magnetic field is something which we are contemplating. How to place the things together.
Okay. Reasonable. Thank you very much. Thank you. Okay, Vladimir Wax, next lecture. It will be applications, but I think also some equipment. Are you going to discuss quantum cascade lasers? Quantum cascade laser which? Okay, quantum cascade laser also will be discussed. So, what time?
I would like to present my talk in Russian because in the second part of my talk there are many biological, chemical substances, and to call them in Russia it's not easy for me, but for English it's non-real. So I would like to present our talk about application our spectrometers for investigation, for исследование биологических пленок для диагностики разных патологий, заболеваний, болезней, лор-болезней, ухо, горло, нос. Вот. И фактически работа направлена на такое развитие метаболического подхода в диагностике, который сейчас становится преобладающим, и в то же время он позволяет вот, создать некий набор маркеров, и это цель работы, создать некий набор маркеров, метаболических маркеров, которые позволяли бы диагностировать, лечить, контролировать лечение и так далее. Потом расскажу про линейку терагерцовых спектрометров, вот, и в заключение представлю некие измерения тканей и биопленок, которые образуются на этих тканях. Сейчас метаболическим всяким исследованиям уделяется огромное внимание. Под метаболом понимается вот полная система различных химических соединений, которые возникают внутри организма, и не только внутри организма, но и всяких биологических и прочих жидкостях. Вот в настоящее время довольно много групп в мире работает на эту тему, считают, что актуально это построение метаболома человека, который позволит предсказывать заболевания, лечить правильно и так далее. Вот. Значит, такой типичный подход к развитию метаболической диагностики – это диагностика, на Западе это называют volatile organic components, фактически это обломки различных биологических молекул, которые можно определить в выдыхаемом воздухе, в биологических жидкостях и так далее. Так вот, эти volatile organic compounds, они имеют весьма маленькие размеры, зато их очень много. И их интенсивность, этих вот компонентов, фактически очень невелика. Поэтому диагностика таких вот это весьма деликатное дело. Вот. Я на всякий случай не хотел напомнить, почему терагерцовый диапазон. Просто так устроена жизнь, что большинство молекул, удивительно важных и для радиоастрономии, и для медицины, и для высоких технологий, они имеют наиболее интенсивные спектры в терагерцовом частотном диапазоне. И сам диапазон весьма широк, он фактически сейчас отобрал дальний К и микроволновый диапазон, все включено в этот диапазон. И еще раз хочу подчеркнуть различие между высокого разрешения и низкого разрешения, невысокого разрешения. Вот это случай, это случай, когда вот спектральная...
Не видно, я проверял. Она принципиально не показана. Я пробовал наводить, заставляет подходить.
Вот я тогда пальцем, с вашего позволения. Итак, вот это профиль линии НО молекулы, а это условно ширина линии генератора, который взаимодействует. По крайней мере, как минимум 1,5 порядка, она должна быть уже, чем ширина спектральной линии. А вот здесь вот это вот выпрямленный фотопроводящей антенной импульс фемтосекундного лазера. Он успешно покрывает полный спектр. И, конечно, когда говорят, мы с помощью time-domain спектроскопии, каких таких методов исследуем, это вызывает некое изумление. Вот. Несколько слов предельно упрощенно о том методе, на котором построены приборы. Это эффект свободно затухающей поляризации. Он в народе называется вращательной релаксацией. У него много названий, но смысл в предельно качественном упрощении предельно простой. Если импульс взаимодействует на резонансной частоте с системой молекул, то в образце наводится поляризация. И вот распад затухающей поляризации является сигналом. И этот сигнал, он во временной области, затем можно сделать фурье преобразование и получить классический спектр. Вот такой подход реализуется у нас двумя способами. Во-первых, переключается фазу переключения несущей частоты, когда за времена много-много меньше времени релаксации фаза несущей перекидывается 0π. И такой подход обеспечивает наилучшее приближение к теоретическому пределу чувствительности и позволяет вот исследовать низкоинтенсивные спектры молекул. А на приемник приходит вот такой набор экспонент от распадающейся поляризации. Другой вариант прибора – это то, что называют на Западе сейчас ЧИРП, а в классической литературе он называется фаз-свип или быстрое свипирование, быстрое прохождение. Опять предельно упрощая все, можно сказать, что за времена много меньше, чем времена релаксации, излучение свипирует через профиль линии, и оказывается, что тут тоже наводится поляризация, причем достаточно большая. И это позволяет также вот диагностировать спектр. И достоинство состоит в том, что можно регистрировать короткоживущие объекты и за короткие времена свипировать по диапазону. Вот, значит, для работы была собрана система линейок спектрометров. Вот этот спектрометр работает с фазовой манипуляцией. Он, как правило, настраивается на частоты линий с очень плохим отношением сигнал-шум, чтобы продетектировать и понять на самом деле, что это за вещество. А все остальные приборы работают в режиме быстрого прохождения. Вот здесь полупроводниковый спектрометр, он работает с одной стороны в диапазоне 110-170 ГГц, но на выходе вот этого замечательного удвоителя весьма приличная мощность, и он нагружается еще на умножитель, по крайней мере, до 700 ГГц. Эта машина работает вот в исследовании спектров. Выше 1 терагерца такой вот синтезатор на генераторе Гана собран. Вот. А здесь умножитель частоты на полупроводниковых сверхрешетках. Ну, он работает до 2,8 терагерц, но начиная примерно с 1,8 терагерц надо уже холодный приемник, потому что интенсивность гармоник маленькая, и поэтому вот он реально на комнатной температуре до 1,6-1,8 терагерц работает. Ну и, значит, диапазон 2-3 терагерца – это квантово-каскадные лазеры. Вот здесь представлен лазер непрерывный лазер на 2 терагерца, около 2 терагерц он работает для того, чтобы, уж не говоря о стабильности частоты, спектральной частоте сигнала, но чтобы как-то излучение там подвести к частоте линии поглощения, ведь здесь нет ни частотомеров, никаких таких приборов, которые облегчили жизнь. Вот приходится сделать фазовую стабилизацию, автоподстройку, основанную вот на таком опорном синтезаторе. Вот. И здесь он фактически успешно, так сказать, прошел вот испытание. И вот здесь вот представлено вот это вот голубенькая или синенькая, это пустая кювета, а это вот линия метанола вблизи 2 терагерц. Вот. А этот вариант мы практически не применяем, когда используется стабилизация по линии поглощения газа, автоматически частота устанавливается равной частоте этого перехода, и сюда многокомпонентную смесь, и можно сразу, очень сложно в настройке, и не каждый может работать. Вот. А практически используется вот такой вот квантово-каскадный лазер импульсный, и оказывается, внутри лазерного импульса есть быстрое свипирование частоты. Причем оно как бы автоматически получается. Это не рукотворное, как вот в субтергерцовом диапазоне, оно фактически автоматом получается. И вот здесь вот в классической такой временном спектроскопии, в временном разрешении, вот это вот временной отклик на муравьиную кислоту, это вот во времени. Дальше видно, что линия имеет весьма непростой характер, потому что там ситуация такая, что возбужденный переход излучает на фиксированной частоте, а частота генератора, она свипирует очень быстро. И получается, что промежуточная частота, она все время перестраивается. Отсюда и возникают какие-то проблемы. Но они вообще решаются, и все это достаточно проходимо. Ну вот, а теперь я перехожу к конкретным вот исследованиям, которые мы проводили для фактически от десятков гигагерц до терагерц, вот для таких многокомпонентных газовых смесей с целью найти маркеры заболеваний у гор нос и вот их патологий. Ну, работали с 3 тканями. Это вот относительно здоровые слизистые, киста в верхней челюстной пазухе и полипы в клиновидной пазухе. Вот. Вот нам привозили такие куски тканей. Вот. И, значит, дальше мы с ними работали, изучали. Вот. Выяснилось, что во многих практически вот эти вещества, которые здесь представлены, я не буду их называть, вот, они все практически имеют быть во всех этих 3 веществах. Но есть и отличия. И вот здесь я покажу такое то, что вот намерили. Вот здесь относительно здоровые слизистые. Вот здесь вот молекула, которую ацетилальдегид, CH3, CHO, вот эти 2 линии здесь, оказывается, они есть во всех 3 тканях. Вот. А есть и, скажем, отличия, которых нет, вот например, которых нет вот в кисте, когда здесь появляется, скажем, меркаптан. И так вот можно найти отличия в спектре во всех 3 тканях. А здесь фактически по вертикали отложено число линий поглощения. Это, грубо говоря, вещь пропорциональной интенсивности. И здесь представлены, значит, вот голубенькая — это относительно условно здоровые слизистые, а вот красненькая — это полип, а зелененькая — это вот киста. И вот видно, что много общих и отличия как по интенсивности вот всех этих вот по интенсивности, так и появляются отдельные какие-то компоненты, которых нет, вот, например, других. Ну, вот, например, метилкарбамид, ну и так далее. Вот. Теперь, значит, это касаемо тканей. Теперь я перехожу к детектированию биопленок. Это фактически вот 4 типа бактерий или бактериальных пленок, которые для лор важны. И наиболее такая распространенная, которая там почти половину контролирует, это золотистый стафилококк. И вот эти под биопленкой понимают колонию, ансамбль бактерий, которые цепляются друг за друга и цепляются к поверхности. И потом они успешно размножаются и имеют вообще такую защитную пленку. И чем они, так сказать, плохие, эта ситуация обусловлена тем, что они не пропускают лекарства к больной ткани. Поэтому вот достаточно важно разобраться с этим вот состоянием. Значит, вот здесь представлена вот аденоидальная ткань, термораспад ее, и относительно здоровая слизистая оболочка. Вот видно, что насколько аденальная ткань содержит много всяких веществ, которые, вот, например, которых нет в относительно здоровой ткани. И так, ну вот здесь такой активный газ, который называется фуран. Вот, он является таким однозначным маркером вот, аденоидальной ткани. Вот. А здесь значит, вот золотистый стафилококк и аденоидальная ткань. Значит, и вот эта пленка золотистого стафилококка, она была на вот, аденоидальной ткани. Значит, вот эту пленку выделили и, значит, отдельно исследовали саму ткань и вот пленку. И вот что видно на этой картине, например, резкое возрастание вот, линий некоторых веществ, аланина в частности, для вот, золотистого стафилококка. Ну и также есть некие вещества, которые содержатся только в аденоидальной ткани. То есть это позволяет робко надеяться, что это могут быть вот маркеры, которые фактически можно будет использовать. Вот. А здесь просто взяли последовательно все 4 вот, биопленки, и вот здесь представлен тот анализ, который был проведен. Ну, очень трудно тут все как бы долго рассказывать, но смысл такой, что есть отдельные вещества, которые позволяют привязаться к тому или иному типу вот, биопленки. Ну и в заключение я хотел сказать еще, что вообще тут очень интересное приложение, я не про медицину говорю, а про технику и физику. Вот мы регистрируем... Сколько еще? Все?
Нет, я просто захотел рядом с тобой постоять.
Ну, сделай милость. Вот, здесь очень интересные задачи, которые касаются, вот, физики и техники. Во-первых, в самое ближайшее время мы рассчитываем подключить сюда ИК-спектрометрию с квантокаскадным ИК-лазером. Вот. Это позволит и упростить идентификацию. И дело в том, что вот вся спектроскопия вращательная, она работает с полярными молекулами. Но ниоткуда не следует, что в том термораспаде нет молекул, у которых нет дипольного момента. Поэтому мы можем тут много пропустить. А они, как правило, их можно детектировать, но требуется колоссальная чувствительность, потому что очень низкоинтенсивные переходы. И что еще я хотел сказать, что и для меня это наиболее интересно, что это повышение быстродействия. Вот у нас сейчас излучение свипирует через профиль линии, ну, скажем, 10 наносекунд, например. Ну, так много я говорю, вот 10 наносекунд. Оказывается, не все вещества мы успеваем поймать даже за такие времена. То есть вот повысить быстродействие, это вот будет актуальная задача. Все, спасибо за внимание.
Спасибо. Ну, теперь можно постоять, да? Теперь можно, да? Спасибо. Какие есть any questions? Пожалуйста.
Вы исследуете молекулы в газовой фазе, то есть спектроскопию поглощения, а бывают, например, соединения, которых очень мало. Используете ли вы какие-нибудь усиливающие среды? Усиливающие, например, ну не среды, а, например, метаповерхности какие-нибудь. Это первый вопрос. А второй, вот эти тергерцовые технологии в медицине, насколько реально, что они в ближайшем будущем могут быть широко используемы? Ну вот, хотя этим занимаетесь, но это интересно тоже.
Понятно.
Спасибо.
Вот как так получилось, что мы сразу отказались от всяких усиливающих средств, потому что мы вообще ведь ловим то, что не знаем, что мы ловим, да? И внесение всяких вот дополнительных устройств или там приспособлений может запутать дело. Поэтому, ну его нафиг. Понимаете, проблема не в чувствительности. Чувствительности хватает. Я говорю, что вот мы можем терять на быстродействии и терять на неполярных молекулах. Вот. А что касается вот, Что касается второго вопроса, он вообще уже давно имеет ответ, потому что масса приборов терагерцовых, она сейчас уже вот реально существует, и мы вот сделали несколько спектрометров с фазовой манипуляцией. Вот один работает в Италии по диагностике рака кожи. Вот. Несколько приборов в Штатах работает. Вот то, что касается нашего спектрометра, он сейчас, значит, вот внедряется в инновационном проекте для как называется, хотят сделать его компактным, чтобы у нас скорую помощь можно было поставить. Затея, на мой взгляд, более чем дурацкая, но деньги дают, и мы стараемся. Вот. Пожалуйста. Что? Еще как востребовано. Вы понимаете, если был на чем делать, можно было бы на Западе востребовано. Вот мы поставили в Японию, там, например, в Германию, во Францию, в Израиль, дофига поставили, но сейчас просто с элементной базы представлять какие, ну и там же еще границы есть. А этот товар, который в терагерцовом частотном диапазоне, не так просто все.
Сергей.
Ну что не спросить? Конечно, конечно. Да, да. Дело в том, что вот следуя Наполеону, который говорил, что для войны нужно только 3 вещи. Деньги, деньги, еще раз деньги, да? Я без претензий. Так, ну, конечно, это очень... Это вы все правильно, только вот... У нас есть и многочастотные спектрометры, и там проблема, например, вот кювет, который мы делаем, они быстро, так сказать, на стенках оседает вот продукт термораспада. Ее надо мыть и сильно прогревать. Вот у нас все старые кюветы, которые мы работаем, они из японского кварца. Японский кварц не боится там, до 600, до 800 градусов нагреть, они спокойно и восстанавливают, все прекрасно. Вот то, что у нас было из гуся хрустального, они при вот таком нагреве начинают как-то вот искажаться немножко. Ну а где сейчас японский? Поэтому вот было бы вот... Мы сейчас приобрели многопроходовую кювету из Питера. Вот. Эта многопроходовая кювета, она позволяет как-то избавиться вот от стенок, чтобы было... Ну там зеркала зато есть. В общем.
Галия Хасановна, прошу вас.
У меня таких 2 разных вопроса. Значит, вы исследуете газы, да? То есть то, что у вас испаряется над тканью, да?
Да.
То есть не сами ткани, конечно же, да? Но тем не менее, не кажется ли вам, что слишком узкие спектральные линии вы видите? Ведь молекулы крупные, анизотропия там может быть в разных направлениях, разный отклик по частоте. А у вас безумно узкие линии на таком прекрасном приборе.
Ага. Ну вы сразу оба или еще?
Ну, все очень здорово, но почему они не выпускаются коммерчески, такие приборы за рубежом, там, где деньги как у людей есть? Вот, поэтому я бы хотела сказать, скажите немножко о недостатках.
Ха-ха, какая хитренькая. Значит, я сначала на первый вопрос. Вот один выдох человека в соответствии с современными так, взглядами, и вот, к сожалению, Юрия Владимировича Киснева я не вижу, он сейчас плотно занимается выдыхаемым воздухом, это 1000 газов. Вот эти вот volatile organic compounds, которые имеют, как сказать, маленькие концентрации, так как это органические молекулы, то, естественно, там у них переходы низкоинтенсивные. И вот в таком рое разобраться, это весьма деликатное дело. И они так весьма близко друг к другу лежат. И вот если иметь широкий спектр, то можно просто не начинать это дело. Хотя есть всякие методы обработки, вот, и люди умеют как-то различать. И у нас вот у меня двое хороших программистов, но я как человек уже не молодой, не очень верю во все эти дела. Вот. А когда узкая линия, я последовательно разрешаю все линии. И вот еще, слава богу, у нас были вот работы с военными, когда там боевые отравляющие вещества типа люизита, да, и у нас никаких проблем не было с разрешением линий. Поэтому тут такое достоинство. Другое дело, если так степ-бай-степ идти, да, то это безумное время надо просто для анализа. И тут я с вами согласен. Но вот плата за безумное время – это либо быстрый его свип такой, максимально быстрой скорости, а здесь начинается проблема детектирования. Вообще шотки диоды, они довольно быстродействующие, там пишут по крайней 15-20 фемтосекунд могут они. Ну, проверить я не могу это, но приходится верить. А дальше начинается цифровая регистрация. Здесь все не так просто. Вот. И разрастается такой пук проблем. Вот. Если я ответил на первый вопрос, но я старался. Ну, так.
Уже нет времени все равно. Можно продолжать. Скинуть презентацию хочешь.
Да, ну просто второй вопрос, почему не выпускают ваше ноу-хау никому неизвестно?
Вы знаете, ведь дело в том, что это вопрос очень такой болезненный. Объясню. У нас в Советском Союзе и какое-то время после распада в Истоке, во Фрязино, производили уникальные источники, лампы обратной волны. И аналога им просто нет. Я во Франции работал с карсинатроном. Просто жалкая подделка. Стыдно смотреть на все это дело. Вот. Они вообще на весь мир расходились, эти лампы. И они фактически до 1,5 терагерца довели. Причем даже лампы делали с военной приемкой, потом это все рухнуло. Понимаете, и когда встает вопрос «сделай», встает вопрос, а где, из чего я буду делать? А полупроводниковая база, она такая достойная, в основном на Западе. И вот как мы, скажем, во Францию, я поехал с 2 сотрудниками, и там у них в Монпелье прямо вот собрали спектрометр, запустили, показали, как он работает. Сейчас они публикуют статьи поперек нас. Вот. Вот. Я не знаю, ответил на ваш вопрос или нет, но вот ситуация такая. А с другой стороны, понимаете, вот мы же не академический институт, и у нас нет лицензии на производство вот, железа.
Галина Александровна, я считаю, что просто не надо их производить. Вы знаете, вот я могу сказать такую историю. Когда был как говорит моя дочка, говорит, молодой, красивый, с усами, так, вот, я был студентом, так, и у нас в лаборатории стажировался Петр Баумрук такой. Сейчас он директор института физики в Праге, так. Вот он говорит, что над лабораторией, где занимаются спектроскопией, все спектроскопии, ну, появится большой плакат. Здесь работают большие шарлатаны. Вот. Я всю жизнь был убежден, я могу сказать, я в Хлебном, что то, что вот эти маркеры, все это большое шарлатанство. Ничего другого. Так? Ну, на уровне кончиков пальцев, там, я всегда так считал. Так? Но понимаете, в чем дело? Появляются люди, которые убеждают. Я дошел сейчас до точки, считаю. Теперь в Шатуре, пока мы сидим здесь, уже ведутся измерения на эту тему. Так? То есть под влиянием Владимира Лейбовича, так, и Юрия Владимировича Кистенева в Шатуре сейчас начинаются измерения спектроскопии высокого разрешения в интересах там, всяких проблем Байкала. Так? Ну, я так подумал в конце концов, ну широта, ну почему бы нет? Уже это так интересно же, правильно? Вот. А если представить себе, вы купили прибор, ну вот этого интереса нет. Нету человеческих отношений, понимаете? Нету авторитета вот этих волшебных рук экспериментаторов, понимаете? Это же...
Вообще буржуи делают сейчас такие спектрометры. И вот то, что у них ЧИРП называется, в нашем понимании, быстрого прохождения, да, у них довольно достойные приборы. И мне пока на рецензию присылали статьи такие. Ну, в общем, они там такой известный деятель Делючи, профессор, очень известный во всех кругах. И у него есть парень из Института спектроскопии, Медведев. У нас есть совместная работа с ними, но они вовсю это гонят, вовсю. И они так иногда спрашивали раньше, а как у вас тут сделано? Вот. Говорю, правильно сделано.
В этой ситуации мы идем всегда в первый отдел и спрашиваем, что нам ответить на вопрос, как это у вас тут сделано.
Да. Ну, спасибо за внимание.
Спасибо. Спасибо. Здорово. Пошли? Ням-ням.
Вы хотите, если есть, то идемте, я вас провожу всех.
Куда?
Кушать пойдете или нет?
Так вы во сколько?
Отлично, спасибо большое. Значит, меня зовут Сергей Тарасенко, я из физико-технического института имени Иоффе, и мы начинаем нашу послеобеденную секцию. Значит, сильно мы не можем затягивать, поскольку мы иначе не успеем на экскурсию. Then probably I'll switch to English. So it's my pleasure. We have a special session. Many invited talks, and the first talk will be given by Dr. Gleb Katyba from Institute of Physics States. The title is Terahertz Wave Delivery and Super Resolution Imaging Using the Sapphire-Shaped Crystals. Could you please start the presentation?
Yes. Dear colleagues, I'm glad to see you, and today I will tell you about our last achievements in the Terahertz elemental base designing. At first, I want to show you our research team and our collaborators. We have good collaborations with BMSTU in Moscow, with MIPT, with Caltech, with Polytechnic Montreal, and many other institutes in universities. And today, at first, I will tell you about the Terahertz waveguiding in sapphire-shaped crystal and its applications for super resolution endoscopy. And the second part of my presentation is this investigation of moisture absorption by the porous opals. I don't want to stay in detail in the properties of Terahertz radiation. It's well known for all of us. It's some slides, but in 4 minutes I strongly recommend to find and look this interesting review for Terahertz applications. This one, some significant review in size, but maybe it can be useful. And another slide for this Terahertz wireless communication, interesting article too. And for Terahertz radiation existed some problems. One of them is the absence or absence of the elemental optical base for Terahertz radiation. Some elements is not relevant, no cheap. For example, Terahertz for Terahertz waveguides, you can't buy in anywhere commercial available waveguides with low losses, low dispersion, and it is interesting field of study to develop Terahertz waveguide. And we have some achievements in this field. We propose Terahertz waveguiding in shapes of sapphire crystals, and you could see some waveguides, arrow waveguides or photonic crystal waveguides, several interesting photos. It has relatively low absorption, above 1 or 2 decibel per meter, some pictures on left and right. And it's very good characteristic for Terahertz radiation. We could develop some endoscopes or for biomedicine or other devices based on such waveguides. Existed for these waveguides some disadvantages. This one have a high diameter, almost 24 millimeters. It's for endoscopes or for practical using, it's too high. And we tried to develop some smaller waveguide. For example, we could use only a hollow sapphire tube. Sapphire has a slow absorption of Terahertz and a high refractive index, and radiation strongly propagate in the central hole channel. You could see some illustration of Stepanov technique. We use it for sapphire tube production without any drilling, any polishing, with atomically flat surfaces. And such waveguides demonstrate in simulations good properties. It has higher losses than previous ones. several tens of decibel per meter, but it's enough for some practical applications. And this in this slide you could see the experimental results of absorption coefficient study in this 3 type of waveguide. For example, it's only examples, waveguide without any cladding and waveguides with polymer cladding. It's additional properties to create Fabry-Perot resonators in the cladding. It's arrow waveguides, and in the some frequency ranges below 1 terahertz, we obtain relatively low absorption, several tens decibel per meter. It's enough for some purposes. For example, we decided to develop a terahertz endoscope based on such small waveguide, because waveguides has diameter less than 10 millimeters, 6 millimeters in diameter. It's more suitable for endoscopic applications, and we tried to perform a terahertz endoscope based on such waveguides. Its endoscope has a super resolution and need for us to solve the complex task to improve the terahertz spatial resolution, because we have some problem with the terahertz imaging system with high wavelengths. We have the able limit opportunity of terahertz imaging. The spatial resolution very low. This one upper limit, and wavelengths, basic wavelengths has several hundred microns. It's too many. And existed some modalities for improving the resolution, but we decided to combine the solid immersion principle for obtaining the super resolution and such endoscope. We fixed the small sapphire solid immersion lens in the end of such endoscope on the sapphire window. This one, it's a scheme, and we suppose that we will obtain the small caustic field behind the such endoscope, and this is results of some numerical optimization of geometry of such lens. You could see the picture in the top left. It's a scheme, and on waveguide with such characteristic, we tried to create such endoscope. And in this picture, you could see the photo of device. It's a waveguide with polymer cladding, and what this one? It's a sapphire window with sapphire solid immersion lens. And the numerical simulation show that we will obtain a very small sub-wavelength resolution, 0.15 wavelengths, and wavelength was 500 microns. And what shows the experimental investigation, we use the imaging system based on backward wave oscillator, and for visualization, it's experimental picture using the 2D imaging scanning using the scanning aperture. We really obtain the small caustic field, this one, for waveguide with sapphire window. And for characterization of endoscopes, we use the 1D imaging using scanning razor blade, and really obtain the resolution parameter near the 0.2 wavelengths. It's relative. It's agree well with our simulations. It's really we obtain the endoscope with super resolution. It's a good result for us at the signal to noise ratio. Only 1.6 times smaller is compared to the empty waveguide. It's as good. And the next, what time does timer mean? How many?
So about 10 minutes.
Oh, it's good. Yes, it's good. I do it. And the second part of my presentation is investigation of moisture absorption by artificial CO2 particles. And what does I mean? In recent works, we developed a new tunable Terahertz material with tunable properties. Namely, it's opal matrix, artificial opal matrix, based on the nanoparticles, silicon dioxide nanoparticles sedimentated in lattice. This one picture is illustrate the manufacturing process, and after sedimentation we took these monolites and take it in the heater, and by the thermal treatment we could anneal some this material and obtain different Terahertz optical properties. You could see in this pictures its optical properties of opals based on different different globules. It's not so significant now. For example, you could see on N dependence from frequency for opals annealed on a different temperature from 500 Celsius to 1000 Celsius, and these opals save their globular structure. But for Terahertz, it's almost homogeneous media. This particle has several hundred of nanometers. It's for Terahertz, it's almost homogeneous media. But we could change and tune the optical properties of such opals. For example, in photo, you could see different type of lens, conical like hexagon and cylindrical lens annealed in different temperature, and it's different material, and it's seem very good, because for Terahertz we have only several materials, polymers or crystals, which could which characterized limit lists of N or alpha. It's very good when we develop such a material which can be change their characteristic. But we have a problem, because this globular globular opals and globules strongly interact with water. This opals obtained by the sedimentation in the water solution, and you could see inside the globule the water is present, and this globules could absorb some water on the surface. It's a complex physical process. We have molecular water, we have bound channel water inside opals, and this water, of course, change the optical characteristics, and it could harm the Terahertz applications due to changes of the material parameters only in room conditions due to humidity. And we try to study this process. We perform some measurement using our Terahertz time spectrometer with a special sample chamber, when we could create a controllable humid atmosphere. This parameter, you could see relative humidity was 82%. And in first, we measured the dried opals, and after that, we open the air inlet and perform the several continuous measurement with some time step, 4 minutes, I remember. And before the process was saturated, you see that dried samples, it's this one and this one. We investigate, I forgot to say, we investigate opals of different type, different particles. This core shell-like particles. It's several core and several shells. And some particle berry-like without any cladding. It's two types of opals, and you could see when it was dried, there was no absorbance and very high Terahertz signal. This one, and spectra. And after moisturization, the Terahertz signal become very light, become smaller. And interesting that for optical properties in the visible range, not significant, not change significant. But for Terahertz, we see the Terahertz properties was changed. And it's a complex transient process for water absorption. You could see that we have some time before saturations begin for both time of opals, for dielectric constant, for conductivity, and but after saturation, the dielectric characteristic almost constant. And what we can, how we could study the adsorption kinetic in such opals. We tried to use the well-known sum rule. It's a consequence of charge conservation law to evaluate the number of adsorbed H2O molecules. This parameter n, it's number of molecules, but we couldn't, of course, know about it. We only know the trend, general trend, using this equation, difference between the integral conductivity. And it's like this one, some result. You could see we obtain some saturation and rising strongly for low temperature opals. We compare the opals annealed and for low temperatures 20, 200 and 400, and for high temperatures 800 and 600. And you could see for high temperatures the saturations began very quickly, and we could use some absorption kinetic models, well known. It existed many types of absorption kinetics. For external diffusion, it's diffusion mainly in the surface of globules, or some internal diffusion, it's inside the globules. And for us, interesting that the standard pseudo first order model or exponential model, it's not suitable for us for low temperatures. It's a more complex process, and we use the same model, stretch exponential model. It's not physical, but semi-empirical. It's more good. And in the result, you could see some conclusions that for both types of opals, the n decreasing correlates with collapsing of material porosity when we increase the temperature of unhailing. And other main conclusions, the porous optical materials should be designed, synthesized, and processed and saved from water using some achievements on the polymer coating or other. And this all, please.
Thank you very much. We have 2 minutes for questions. Please, questions. Maybe I will start. Why did you choose sapphire and to produce these waveguides?
Yes, interesting questions.
Sapphire is quite expensive.
We tried to solve the main task for Terahertz waveguiding, this slide, because most of waveguides based on polymers, but polymers has yes, flexible. It's advantage, but in disadvantage, the polymers sensitive to the environment. And for example, if you want to use it in biomedicine, when we try to sterilize our device, or in some aggressive media, or in something else, when we have a negative environment, the polymers is not so suitable. Another reason, sapphire has a higher refractive index, higher than 3, and only a frontal reflection from walls, it's take for us a good advantage in this comparison of polymers. Existed and another non-obvious advantage when we use sapphire. It's atomically fluid surfaces when we produce sapphire by Stepanov technique, and so others some.
Okay, thank you. Other questions? Yeah, short question and short answer.
How do you reduce reflections from the opposite ends of waveguides?
Excuse me?
How do you reduce reflections from waveguide ends?
Yes, it's really we use a backward wave oscillator. It's a relatively a source of relatively powerful power radiation, and we didn't take any modalities to reduce, not просветляющее покрытие не использовали, но и другие есть, да. Все-таки сорвусь. Ну, тут, да, это пока первая работа, тут такого не было. Yes.
They just do not care. Okay, thank you very much. Thank you. The next talk will be given by Alexey Kazakov, Dr. Alexey Kazakov from Moscow State University. It will be about non-equilibrium transport and mercury telluride based heterostructures induced by terahertz laser radiation. 20 minutes, 15 plus 5 for discussion.
So, good afternoon, dear colleagues. Well, first, my gratitude to the organization and programming committees for an opportunity to present this invited talk here in the conference. And today I will talk about our recent research devoted to the study of the non-equilibrium transport in topological phases based on mercury cadmium telluride solid solutions. And we actually utilized for this purpose the high-power terahertz laser radiation. But first, I'd like to introduce you our team that included scientists from different organizations and even different countries. So all the research and analysis work were primarily done by Moscow State University group.
You are currently the only person in this conference.
Measurements were performed in Regensburg, in the University of Regensburg, the Terahertz Center, led by Professor Sergei Ganichev, and also our high-quality MCT, I will call the mercury cadmium telluride just MCT to be shorter, samples were synthesized in Novosibirsk, so special thanks to Sergei Dvoretsky and Nikolai Mikhailov. And finally, the processing of the samples were performed in Lebedev Physical Institute. Well, here is the outline of my talk. After, brief introduction, I will move to the discussion of experimental results and two important sections. First, asymmetric terahertz photoconductivity in MCT samples, and the second, non-local terahertz photoconductivity in the same samples. Let me begin. Topological insulators, being a relatively new class of the materials, possess a set of unique physical properties. So first, they behave as an insulator in the bulk, and necessarily they possess conductive low-dimensional states on their surface in 3D case and on their edge in 2D case. Also, the charge carriers in this topological, let's call them this states, possess a quite high mobilities, and their spin direction is strongly coupled to their momentum direction due to strong spin-orbit coupling in these materials. well, what is important is that the main experimental technique, the main approach to study these topological states and topological materials is angle-resolved photoemission spectroscopy, which explicitly demonstrates the direct dispersion relation of these surface states. It can be seen from here. But the disadvantage of this approach is that it provides a very limited information about the transfer properties of these topological states. At the same time, most of the 3D topological insulators possess quite high bulk concentrations of charge carriers, and the task of extracting the contribution of charge carriers being in topological states into the whole transport is quite a difficult task. So, in this sense, the mercury cadmium telluride or MCT solid solutions possess a huge advantage because they can be synthesized with a relatively low bulk carrier concentrations. And this actually allows us to study the photoconductivity in terahertz range in these systems. What is important that composition-driven topological phase transition in these materials occurs at 0.16 cadmium content. And also, I have to mention that the characteristic energies of energy spectrum of these solid solutions correspond to terahertz spectrum in the vicinity of the transition point. So this is of particular fundamental and practical interest to study the photoconductivity in these solid solutions, in particular terahertz range. Well, the samples that we studied were synthesized by means of molecular beam epitaxy in Novosibirsk on a semi-insulating gallium arsenide substrate. You may see the structure here. And to make it clear, we studied both topological and trivial phases of MCT solid solutions. What does it mean? To make it clear, the topological phases of MCT solid solutions correspond to inverted energy spectrum in the left part of this diagram. And well, trivial phase of the MCT solid solutions correspond to direct energy spectrum that locates somewhere here in the right side of this part. So we studied them both to compare. And what is also important here is that the concentrations of bulk charge carriers were indeed relatively low, on the order of 10th to 14th power of reverse cubic centimeters. Here is the last slide of the introduction, and here you can see the experimental setup. So it consisted of two lasers. The first one is CO2 laser pumping one, and the terahertz gas laser with an ability to switch gases to obtain different wavelengths. And also here you can see the typical kinetics of terahertz radiation that we utilized. All the experiments, both transport ones and photoconductivity measurements, were performed in a standard Faraday geometry. That means that the magnetic field was applied perpendicular to the sample surface, as it depicted here, as well as the terahertz laser radiation. And last but not least is that all the measurements were performed in a 4-probe configuration, with 2 potential probes and 2 current probes. So let me move to the results. First, we studied the photoconductivity in MCT heterostructures without any magnetic field applied. And there are some important points. The first one is that the kinetics of the photoconductivity possess a complicated profile. So apparently it contains some different contributions from different parts of the structure. Second point is that the photoconductivity possesses different sign for structures with inverted energy spectrum corresponding to topological phase. It is positive actually, and it is negative for the structures with a direct energy spectrum corresponding to trivial phase. And one more thing is that the effect we observe are indeed the photoconductivity effects. Because if you look here, for example, when we switch the sign of the bias, electric bias that we apply to the sample, the sign of the photoconductivity, the photoresponse here, is also inverted. And if, for example, we switch off the bias, we do not register any pronounced signal. So let us now introduce a magnetic field into the experiment. And Again, the photoconductivity in this case in the samples with inverted and direct energy spectrum behaves in a qualitatively different ways. So first, in the trivial phase, the direct energy spectrum, samples, the photoconductivity is mainly negative. I will discuss only the first part of this photoresponse. And it's more or less symmetric in a magnetic field. What is also important, that it is, different pairs of potential probes, 7 and 8, for example, and 2 and 3, are equivalent in terms of the photoconductivity. It is important, you will soon see why. Oh. Yeah, okay. Let us try continue with this one. Well, this is actually an important slide. Well, here, the photoconductivity in the topological phase samples is presented. And, well, it may be seen, at least, that the kinetics of the photoconductivity consists of two pronounced contributions. The positive one, that is clearly seen, and the negative one that is, well, not clearly seen, but it's definitely there. And no, it's just, I think this is an effect of the one slide. I hope so, at least, yeah. So, if then we reverse the direction of the magnetic field from this configuration to this one, we see that the positive component of the photoconductivity is strongly suppressed, at least first one, right? And the same, actually, effect may be seen here, but if, for example, we now fix the direction of the magnetic field and switch the position of the potential probes from 2-3 pair to 7-8 pair, so we just move to another edge of the sample, then the positive component of the photoconductivity is again strongly suppressed. So from this we can conclude that the Terahertz photoconductivity demonstrates in the topological phase of MCT samples an asymmetric behavior. And this asymmetric behavior may be clearly and unambiguously seen from the upper part of this diagram. This is the amplitude values of the positive component of the photoconductivity, measured at the different pairs of the sample. And also what we can see from this graph is that the negative component of the photoconductivity is more or less symmetric in a magnetic field. What is important here is that these asymmetric effects reveal themselves only in a non-equilibrium case, so that the magnetoresistivity that was measured without any photoexcitation applied is a symmetric function in a magnetic field. So there is the question, what is the possible origin of this asymmetric behavior? And sampling homogeneity might be the one. So in order to check if it's true, we decided to conduct an experiment with the rotation of the sample around the vertical axis, normal axis to the sample surface, by 180 degrees. So we just switch the position of two potential probes. And from these two graphs, you may see that actually it did not lead to any qualitative changes. So it may be concluded from these graphs that photoconductivity, asymmetric part of the photoconductivity is not bonded strongly to one of the edges of the sample, because it's qualitatively the same for two positions of the sample. So further, in order to find out different contributions and different elements of structure that contribute into this asymmetric part of the photoconductivity, we decided to conduct some experiments with the samples with different thicknesses of active layer. So there is the scheme. And it can be clearly seen from the dependence that the decrease of the active layer thickness leads to, again, decrease of the positive component of the photoresponse we measured. And that indicates the presence of bulk contribution into this non-trivial asymmetric photoconductivity. But in conventional case, the bulk transport mechanisms do not imply any asymmetric behavior in magnetic field. So we expect there to be more contributions from different elements of the structure. And at this point, it's important to remember that in a direct spectrum samples in trivial phase without any topological states, the photoconductivity is symmetric in magnetic field. So it gives us grounds to assume that probably this asymmetric part is somehow related to the formation of topological states on the surface of topological phase. And well, it is well known from this famous work that the electron transport, well, it's in two-dimensional quantum wells, in two-dimensional topological insulators based on mercury telluride, occurs in a non-local regime. So we also decided to check if it's true, to try to conduct some experiments in a non-local configuration. And in our case, the non-local configuration assumes spatial separation of current and potential probes on the sample. And for these purposes, we designed two sets of samples. The first one is a set of whole bars with extended number of potential probes, the 4 pairs. And the second set of the samples is a classical non-local geometry of the sample, is the H bar, similar, more or less similar like in this work, with different linear dimensions. All the other parameters of the experiment were the same, and necessary remark to be here is that all the results that I will present further will refer to topological phase only samples, because in direct spectrum samples, trivial phase samples, we did not register any pronounced non-local photoresponse. So what are the results? Okay. Here you can see on the left side of the slide the graph that depicts the photoresponse kinetics measured in a whole bar samples from different pairs of potential probes. These are indicated for each curve. And on the right side of this slide, you may see the graph that depicts the photoconductivity, the photoresponse kinetics measured in an H bar samples that differ from each other by their linear dimensions. They are also depicted here. And what we can see here is that the photoconductivity photoresponse actually profile does not depend, almost does not depend on the distance between current and potential probes, which is not typical for the bulk transport. And here, on the embedded graph, you may see that the voltage drop measured without any photoexcitation applied decreases rapidly with the distance. So it can be concluded from here that in a non-equilibrium case, in case of photoexcitation applied, there are some additional transport channels formed, additional to bulk ones, and they have nothing in common with bulk transport. And the last experimental slide that I would like to present you is the experiment that we conducted with the whole bar samples. And in this case, we applied the electrical bias to one of the middle pairs of the whole bar, 5-6 apparently. And we measured the photoresponse from different sides of the sample with respect to the bulk current localization area. So we measured the photoresponse from pair 7-8 and 3-4. And from these results, you may see that the sign of the photoresponse is different on different side of the samples.
Hello.
The first. Second, you may see that the photoresponse sign depends on both magnetic field direction and the polarity of electric bias, equivalent to electric field direction. Well, phenomenologically, both the set of results obtained in whole bar geometry, classical local geometry, and non-local geometry could be, again, phenomenologically described as a formation of additional edge transport channels that contribute into the whole transport. And these edge channels, additional to bulk ones, they possess a chirality that is that depends on the both of the on the direction of the magnetic field and the bias polarity. So there are the main outcomes of
You
this
are currently
talk.
the only person
And
in this
to
conference.
briefly repeat them, I will say that first, we studied and detected the Terahertz photoconductivity in MCT samples with both topological and trivial phases. and it possesses different signs for two sets of samples. Second, we demonstrated the existence of the odd in a magnetic field component of the terahertz photoconductivity in local configuration. And last but not least, again, we detected the strong non-local component of the terahertz photoresponse in topological phase samples of MCT thick epitaxial films. So that is all for me. Thank you for your attention.
Thank you very much. So we have time for short question. Yeah, please. Yeah.
Maybe I have a very stupid question, but sorry for that. But how do you exactly determine that you work with the topological phase in your MST sample? I mean, when you study the photoconductivity, the terahertz photoconductivity, because actually every heterostructure, every semiconductor, it shows this very similar behavior. So did you get the question? Yeah.
Of course, yeah. I think I got the question. We also conducted, of course, preliminary transport measurements, and it is well known from the Frederick Tapp works that the temperature dependence of resistivity is qualitatively different for the structures that possess inverted energy spectrum and direct one. So this is how we can just diverse them.
Okay, thank you. Let us thank Alexey again. Thank you. So the next talk, also we have invited talk. It will be given by Dr. Dmitry Ponomarev. The title is Plasmonic Enhanced Terahertz Emission in High Aspect Ratio Metal Grating Photoconductive Antennas.
Yeah, very complicated.
One. Okay. Okay. Thank you very much. Okay. Thank you for the presentation, Mr. Chairman, and thank you the organizers for inviting me. So I will speak about one of the directions that we work on approximately, I think, since 2016 and 2017. Today we have a wonderful talk by Professor Mishina, who talked about the spintronic terahertz emitter, and in this sense my talk will be quite similar, but not about the spintronics, but more to the optoelectronics, and I will speak about the terahertz emitters based on the photoconduction phenomena, and I will talk about one of the okay, I just didn't see on the screen here. Okay, suddenly it disappeared. Okay, I will talk about our cooperation between the My Institute, which I present, and the group of Professor Kirill Zaitsev, who works in the Prokhorov General Physics Institute, and so we have our fruitful, I think, very fruitful cooperation since for long years, so I will start with the benchmarking of what we have right now. So this is just the progress in plasmonic emitters, because actually know that the plasmonic effects and different kinds of the plasmons, surface waves and plasmonic waves and polaritons, they are known for a long period of times, and especially there were wonderful theoretical works in Soviet Union, for instance. But you can see that actually the first experimental work that was done by our foreign colleagues was made only in 2012. And that's funny. And certainly, first of all, this is because we had many technological limitations. And currently, some guys decided that we can what we can do. So first of all, we need to increase the electric field in the near field surface of the semiconductor, so that the photocarriers can contribute immediately to the terahertz emission before they recombine. So the idea is very simple. And the first experimental work was dated in 2012. Then it was like the evolution of what is shown here. And I just can say about about this wonderful work that was made by Professor Jerahi from the United States of America in 2014, and you can see she just introduced the so-called 3D phenomena. What is it? It means that you can etch your semiconductor with such high aspect ratio. And the photocarriers, in this sense, they are localized in the vicinity of the surface of semiconductor. So you have here the photocarriers, you have here the antenna metallization, and so the photocarriers can immediately contribute to the antenna. As I remember, the most conversion efficiency that has been recorded was dated by this group, so it was 7.5%, so it's quite enormous for a single element. Then the same group demonstrated this kind of polarization insensitive meta surface. Why was it done? Because actually you need a T polarized light to excite the surface plasmon waves, like here, but here you can use different orientations of your E vector of the laser radiation to efficiently excite the plasmon. So it's very nice work. And this same approach has been also done when we're trying to move from a single element to a large array emitter, because we need to increase the power. It was a high power laser and high power Terahertz emitter, using also the plasmonic gratings. And the last one is our last work, where we demonstrated our idea. So our idea was not to increase the aspect ratio of a semiconductor, but to increase the metal thickness of the electrodes. And I will speak about why it is important. So first of all, I will start with our relatively old work. It was dated by 2018. And here you can see the example of how the photoconductive antenna looks like. In the presentation of Elena Mishina, it was quite similar sketch of the antenna. So we have the femtosecond laser pulse that drives your photocarriers, and you have the Terahertz radiation pulse. So the idea is very simple. And what we have here is two symmetrically placed metallic gratings. And what is important that these gratings should be should have the dimensions that are less than the excitation wavelengths. And what is interesting that if we're trying to increase the thickness of this metal in this grating, for instance, in one of the grating, we can then plot the dependence of the delta opt versus HP. So delta opt is the value of how you can increase the electric field near the interface between the metal and the semiconductor. So we can see that actually this is the oscillation behavior, which is quite similar for any plasmonic structures. But nevertheless, we can see that there is the maximum that corresponds to the HP ratio, which is 0.5. It means that we have the thickness of about 100 nanometers and the period of about 200 nanometers. So how it looks like in the simulation or in sketch. Then we can move on to the fabrication. You can see here the SAM image of the so-called log spiral antenna. Here is it. And this is like the conventional geometry, and this is the same thing with two symmetrically placed plasmonic gratings. So here the things are the same that we have in this sketch. So finally, certainly, just not to waste the time, I won't speak about some kinds of technology. If you have questions, I'll just answer the questions why we're using some technology to decrease the leakage currents, etc. But certainly we were using some kinds of the anti-reflection coatings, like the first presenter said. And then we can move on to the experimental part of our study. So this is quite a simple time domain spectrometer, which was developed in the Professor Zaitsev group. So one antenna is used as the Terahertz emitter, and the second antenna is used as the Terahertz detector. So quite very simple. And the Avesta femtosecond laser is used certainly as the laser source. So you can see here I depict some of our publications where you can find the detailed information. I won't stop on that. So I just can say only one thing, one important thing, because we additionally developed this like some kind of like setup, I can say, visualization setup, to precisely control the position of the laser spot in the antenna's gap, and so also we can determine the spot size or the diameter. So also we developed a software to this program. We were using just the CCD camera and the LED. So it's very convenient because you can see here is the example. I don't know how it looks like, but I hope it's so. It looks quite good. So you can see the H-type antenna, and this is the laser port size. So we can control precisely. Why is it important? So it is important, first of all, but when we work with plasmonic antennas, because we need to concentrate all our light on one of the grating. It's very important. So now we can move on to the spectral measurements and power measurements. So here is the difference between the conventional antenna and the plasmonic antenna. So conventional antenna, it's not a commercial antenna, it's the same antenna that we fabricated, so it had the same technological routine. But nevertheless, you can see that in the dynamic range, so in other words, it's a signal to noise ratio, there is a strong difference. So the enhancement here is 1000 between this and this. What is also important, so what is the difference between this blue curve and the and black curve? The difference is the average pump power. So in this case, we were using like 10 milliwatt of the average optical pump power, so it's much common for the time domain spectrometers. But what is important in plasmonic antennas that it initially, they provide very high photocurrent, which is good, but on the other sense, it's bad because it can provide a thermal or electrical breakdown. It's a big problem. And what is important here that when we start to decrease the optical pump power, you can see that the antenna also efficiently work. And it is very important because to efficiently work with these plasmonic antennas, we do not need to take high power laser systems. It's very important. So we have the enhancement, we have the overall power, which is just approximately 4 microwatt. It's okay, I got it. And the efficiency of approximately 0.5%, but it's maximum efficiency, certainly corresponding to this part of the spectrum. Okay, so this was the first part of my presentation. The second part, we decided how we can additionally increase the overall performance of our plasmonic emitter. And we remembered that there was really wonderful works by Thomas Ebbison, who just in 1998, yeah, that's right, he presented this theoretical work, and that is called the extraordinary optical transmissions through sub-wavelengths Hall arrays. It means that at the optimized parameters of your grating, you can just provide extraordinary transmission, and it is very important because there is no semiconductor. But if we'll just add a semiconductor under this sub-wavelengths Hall array, it means that we can just generate a lot of photocarriers, and these photocarriers, before recombination, that they can contribute to the Terahertz emission. So what we desire, what we should have, and this work just is the experimental demonstration of that work. So in other words, we have the optical transmission enhancement that is crucial, and in this sense, let's move again back to what I showed in my previous slides. So we have the same construction, but the same topology. But now we just calculate this grating in the correspondence to the maximal transmission of optical light. So what it means? So now we have like the controversion between this 100 nanometer thickness, what I just showed you in my early slides, and this is the same picture. So H is the height of the grating, and P is the period of this grating, and you can see that actually, if we just recalculate the design of this grating according to the maximum transmission of the laser radiation T, which is depicted here, the optimized thickness, the optimized height, or the thickness, it's the same thing, the same things. The optimized thickness of your plasmonic grating is just 170 nanometers. So it's a bit twice larger compared to what we have earlier. So then we can estimate, not estimate, but calculate the other parameters of our grating. So this is G is the distance between the neighboring electrodes in the grating, and V is the width, certainly, of each single electrode in this grating. And you can see that actually the HP now is close to 1, because initially it was 0.5 and now it's 0.8. I can also state that 1 is like the maximum value that we can attain in our technology, because actually when we have in simulations, it's better to increase this H, like to infinity. But actually in fabrication technology, there's the problem, because you have two neighboring gratings, and due to proximity effects after development in your lithography, you have the problems that they just coincide to each other. And this is the problem. You have like this coincidence and no plasmonic works. So actually we can also estimate the losses, because ohmic losses in noble metals is a big problem. Therefore many people comes from plasmonic metal surfaces to all dielectric metal surfaces, but you can see that the loss is just 5%. So it's just a very small value. Okay, so we can also estimate one interesting thing, because in this sense certainly we have this with waveguides, because the height of the metal is just 170 nanometers. So this is like the waveguides, and we have can estimate the Mohs spectrum of this waveguide. So what is interesting here, that you can see that when we are using the grating with high aspect ratio, just 3 minutes or 2 minutes. I promise you I'm not be out of time. And you can see here that approximately one higher order mode is excited in this grating compared to the case for a 100 nanometer thick plasmonic grating. So actually it means, in other words, it means that we can increase the overall power of our emission spectrum. So the taller grating you have is better, but we have the technological limitations, and this value, I mean 170 nanometer or maybe 190 nanometer is the maximum what we can have in our technology. Not only in our technology, but overall technology. So the resonant condition works. So the first mode is excited compared to the case of our first investigation. And we can just switch on to the last slide of my presentation before conclusion. So here you can see the red curve is the grating, which I demonstrated in my first slides of my presentation. So here is the H is 100 nanometer and HP 0.5. And here is the optimized corresponding to maximum transmission, to the maximum transmitted optical light. This is the optimized grating. So we can see here that there is approximately plus 10 dB in ASN ratio, in signal to noise ratio, and there is approximately 10-fold enhancement in the emitter Terahertz power. So overall, I can say that this optimized, I mean this blue curve optimized geometry of this optimized plasmonic antenna, it's just 10 in 4th power. It demonstrates a 10 in 4th power enhancement compared to commercial or to the same antenna without any optimization of the plasmonic gratings or without any plasmonic gratings. So it's quite a very important thing to when we use this antenna in time domain spectroscopy. So here is the summary of my talk, but I think that I just told everything that I wanted. So you can see here are the last thing that I told you. This is the quite strong enhancement. And also I can say that these are results for a single element antenna, but we also will work with the large array antennas. But what is most important here, I can see that this enhancement is observed for a single element antenna, and which do not require any high power laser systems. So that's all. Thank you very much.
Thank you very much for a highly interesting talk. So please, questions. Probably I will start. Could you say about the polarization of emitted radiation? Is it linearly polarized?
No, it's not linearly polarized. Yes, the polarization is linearly polarized, but in plasmonic antenna, we do not actually measure it, but conventionally it has the, like, I don't know, some kind of just maybe.
Kind of spiral
yes,
structure.
yeah, like this. So we have like the central part which is quite integrated, and the edge parts.
But the emission comes from the center.
Yeah, emission predominantly comes from the center. Yeah,
okay,
predominantly.
Okay, other questions? Okay, please, Mishna.
Maximum efficiency is 7%, but plasmonic antenna could not stand the power in comparison with, for instance, organic crystals. So can you tell, please, absolute value of energy in terahertz pulse, and maybe in terms of field in megavolts per centimeter also, just to have impression what is the achievement now?
70.5% was, it's not our achievement, it's the achievement of the Jarakis group. So it's not our result, I mean. I can say, but maybe not in joules, but I can just in microwatts, if it's okay. So overall, when we're using when we were using the Golay cell, we estimate the overall efficiency, the overall immediate terahertz power. It varies from approximately 4 to 10 microwatt in this bandwidth, up to 4.5 terahertz.
Okay, thank you. Other question again? Short question. Short.
Then it was predicted according to your estimations. I saw that the transmission coefficient is increased only twice. Yes, and maybe another effect. I miss it.
Yeah, sure, but actually I can say that the experimental results were a bit poor compared to our theoretical predictions, because actually if we were just simulating the terahertz pulse and then estimating the overall efficiency, it should be much greater not much greater, but it should be greater in our theoretical predictions. But here certainly in our theory we do not just take into account like saturation effects or any saturation effects. I can say that may be the most problematic effect which also occurs in the plasmonic antennas, because also you have the overshoot effects because of the high photic current which is generated, and these kinds of effects that we didn't take it into account in our theoretical predictions. But actually, as we confirmed in our experiment, the idea works and it works well. But certainly there is, I can say that there's just a high to moderate correlation, but it's a very good agreement.
Okay, we have to move to the next talk. Thank you very much.
Thank you.
The next talk will be given by Dr. Dmitry Sobolev from Institute of Applied Physics in Nizhny Novgorod. The title is Laser-Driven High-Power Microwave Compressors. Okay, so 20 minutes, 15 minutes plus 5 for discussion.
Hello. So I present here our work on microwave compressor driven by laser power. So the motivation of our work is a new generation of high gradient particle accelerators, because we have a law of breakdown rate. If we are trying to avoid breakdown, so we may use nanosecond impulses, and for nanosecond impulses we can increase electric field in accelerator up to 5 times. So this could allow us to produce much smaller accelerators with the same accelerating energy. And to achieve such parameters, large field and small duration, we need a source of such microwaves. So these are some experiments with high accelerating voltage up to 200 megavolts per meter. These are small accelerating cells, and the results are quite promising. And for full-scale accelerators, we need the source of such electric field. So the first experiments for close to our compressor devices were done by other groups, and they use silicon switcher, but in our group we prefer to use gallium arsenide switcher because silicon photoconductivity usually have a relaxation time of approximately several nanoseconds, and for shorter impulses, if we try not to use two-step switch which cuts off and front and rear fronts, and we want to use only one-step switch which only cuts first front, and after less than nanosecond we want to our photoconductivity to fade out and cut out the rear front. So and the other problem is stability of frequency. I made another presentation on this conference, and the one of our last results regarding microwave sources, gyrotrons, we stabilized the frequency up to a tolerance of our external clock, and the second step, we fed our high power 1 megawatt gyrotron with relatively low power of our stabilized gyrotron, and the frequency was successfully caught, and so now we have microwave source which can be frequency and phase stabilized with power of up to megawatt. Theoretically in continuous wave, but our test site limits to impulses of several microseconds, because we don't have enough water flow for cooling. So this is the results of external frequency and phase locking by a small medium power gyrotron to a full power gyrotron. And as for the our compressor device, we use a three-mirror system which is fed by gyrotron and a grating which couples the resonator with small coupling, approximately 2% in our experiments, and gallium arsenide switch, which consists of two discs air-spaced, which is transparent when we don't light it up by a green laser, and it starts to be conductive after laser radiation and reflects the compressed pulse to our load. So the total length of the radiator is 700 millimeters, which is slightly more than 2 nanoseconds of pulse, and photoconductivity lasts for less than nanoseconds, so we are cutting out maybe half or third part of the total power which is inside the compressor. As for required laser intensity, we made several experiments with 870 nanometer and 532 nanometer lasers and achieved relatively good results with both, but 532 nanometer green laser is more convenient because it can be made smaller and cheaper. So the required level of laser intensity is approximately 1 millijoule per square centimeter, and it gives us the maximum possible reflection coefficient. So we could achieve this value with a relatively small laser system, which fits on the table and costs not an arm and a leg. So here is on the left side, here is the laser system, and on the right side we have a oscilloscope view of the single laser impulse. Total power is approximately 50 millijoules, and this is enough to light the maximum size of gallium arsenide disk, which we were able to obtain. The diameter is 150 millimeters. We tried to obtain the maximum size of this disk because we need to work with up to 50 megawatts power in our later experiment, and we tried to get the parameters we need to achieve such big power requirements. So these are the main parameters of our compressor system, and here is the compressor with matching optics for first low power measurements. There are 3 main copper mirrors. On the bottom there is a corrugated mirror, and here is the semiconductor switch. These are the schemes of our measurements. For the empty resonator, we got the bandwidth of 2 megahertz, which gives us a Q factor of approximately 85,000. And as for the resonator with switch, not powered switch, we have a resonance bandwidth of 4 megahertz, which gives us total losses per 1 revolution of 6%, which is more than we want, but for 2-disc semiconductor switch, we couldn't get less because we are limited by an existing semiconductor plates of fixed thickness, and we only can get it transparent in 2-disc construction. And here are the results of lower power experiment. The compressor was fed by BWO source, and we achieved saturation on higher side of our laser power, and we measured the compression coefficient by switching the corrugated mirror direction, so as the full source signal was received by our receiver. And after all, here is the signal of oscillations inside the resonator, because we only cut out the half of its power, and the other power still remains inside the resonator, and after several microseconds the resonator is fed up to limit, and we may get a new laser impulse. So we achieved quite a good compression of about 20 to 30 and sub-nanosecond impulse, and the main tasks which should be solved before main power experiment are the manufacture of single wafer switch, which allows us to significantly increase the amplification, maybe twice, maybe something less, and possibly the vacuum chamber for our compressor. And after that we could achieve megawatt level compression in our compressor and get an amplification ratio of approximately 50, we hope. Thank you for your attention.
Thank you very much. So you can see that the range of our session is very large. We have power from microwatt to megawatt. So questions? Probably one short question. Okay, if it's not the case, let's thank the speaker. Thank you. The last but not the least talk will be given by Dr. Maxim Ionin. The title is Broadband Conversion of Multi-Line Q-Switch CO Laser Emission under its double pass through some kind of crystal. I think I'm not sure that I can pronounce that difficult chemical compound.
I'm sorry, but I'm not a doctor still, and
I predict the future.
Yes, the topic is my report. You can see on the slide. My name is Maxim Ionin, and our work carried out by Lebedev Physical Institute, National Research Tomsk State University, and Laboratory of Optical Crystals, LLC. I present gas laser laboratory of Lebedev Physical Institute. Different problems like environmental controlling or controlling of working area requires development of mid-infrared laser sources. And one of the most efficient such these laser sources is a carbon monoxide or CO laser. Another advantage is that its spectral range are within the spectral interval of atmospheric transmission window that may be used to increase final that may be used for remote sensing of different toxic or hazardous substances in air. Also, different dangerous gases are in spectrum range of CO laser. And CO laser generate in two spectral intervals: fundamental band from 4.7 to 8.2 microns, and first overtone band from 2.5 to 4.2 microns. And its cascade mechanism of lasing links to the fact that it has a great efficiency among another discharge lasers. In fundamental band is about 30%, and in first overtone is about 16%. Also, it can generate in Q-switch mode in 150 lines, but different tasks require radiation that go beyond of its spectral interval, and best way to enhance and enrich the spectrum is some frequency generation in nonlinear crystals. Therefore, our motivation is enriching of a spectrum and enhancing the final efficiency of conversion in nonlinear crystals by the radiation of DC pumped carbon monoxide laser in spectral range from 5 to 6 microns. In our laboratory, we tested all these nonlinear crystals for SFG generation, and after comparing the results, we claim that zinc germanium phosphide is the best option for this type of conversion for this CO laser. You can see that entire length of so-called non-critical phase matching fully covered by main CO laser radiation that may be used to increase final efficiency. There are some procedures to increase SFG's efficiency. First is sharper focusing of laser emission, second is using an intercavity SFG scheme, and third is application of double pass scheme, and fourth is application of nonlinear crystal with anti-reflecting coating or air coating. In last experiment, we tried to test crystal with air coating. This research became possible due development of new air-coated coatings to zinc germanium phosphide. And these new crystals has high optical threshold in CO laser spectral range and SFG spectral range. These crystals were covered by air coating, but on both sides by laboratory of optical crystals. And on this slide you can see transmittance of both options of these crystals. For example, is our previous experiment of intercavity conversion with uncoated zinc germanium phosphide. And here the results. You can see SFG power comparing with CO laser power. And now about our last experiment. This is our Q-switch CO laser. It has peak power about 4 kilowatts. Pulse duration is about 1 microsecond. And this is the scheme of the experiment of conversion with air-coated zinc germanium phosphide. It can operate in two options. First option is double pass scheme, solid line, and another option is single pass scheme. This is the crystal where radiation is directed to. In single pass option, dotted line, radiation reflected to the measurement by this spherical mirror 3, and in double pass option, it reflected by dichroic mirror. You can see CO laser and SFG temporal pulse shapes at different rotation frequencies. Blue curve is temporal pulse before the crystal, and red curve is temporal pulse after the crystal. You can see that with enhancement of rotation frequency, curves became more Gaussian. You can see average conversion efficiency and peak conversion efficiency and duration of the CO laser and SFG pulse versus mirror rotation frequencies. I admit that SFG pulse decrease faster than CO pulse. That leads to the fact that average conversion efficiency decreases faster than peak conversion efficiency. Okay, here you can see dependencies of the SFG power and the conversion efficiency on the CO laser average power. For double pass scheme compare with single pass scheme. In both options, final power increased quadratically, but conversion efficiency increased linearly. That was supposed by well-known formula from Handbook of Nonlinear Optical Crystals. This is the gain factor at SFG radiation. you can see that gain factor was from 2 to 3.5, and that fact that it was over the 2 means that second pass provide not just linear but non-linear addition to the final power. And it can be seen also that gain factor decrease with increase C laser power. It may be explained something like frequency conversion saturation or something like that for SFG strongest spectral lines. Here you can see SFG average power and conversion efficiency versus the C laser beam by angle of incidence alpha. Maximum at minus 0.7 degree, and that means that cut angle of crystal not coincide with optimal one for this type of SFG conversion. After that experiment, we decide to check what would change if radiation go back not at direct angle but at slightly different angle beta. And difference appear primarily in spectrum. In first column when radiation go back directly, and second column is when radiation go back by angle 1 degree. And you can see then in this option when angle of incidence is minus 4 degree and angle beta is about 1 degree, we have spectrum that in several times wider and has 3 times more spectral length than in this option. That means that angle of incidence and angle of deflecting beta greatly affects to the final spectrum. And our conclusions: the maximum conversion efficiency in the double pass scheme came up to 10%. SFG spectrum was transformed in the wavelength range from 2.35 microns to 2.92 microns, and the number of SFG spectral lines in the best case came up to 190. Thanks for your kind attention.
Thank you very much. We have time for questions. Yeah, please.
The question about orientation optical axis of the GP crystal in your case. What is the kind of synchronism? What is the axis orientation, optical axis?
Okay, a type of synchronism is
orientation optic axis and polarization orientation of the quantum beam second harmonic.
You know the orientation of the crystal.
yes. Because we know the
what this means? What is the theta?
repeat please.
What is the theta angle?
Theta angle is angle from
Probably between the optical axis.
No, please.
В общем, это угол, это нормально. Вот. Ну, насколько я понимаю, между
как кристалл вырезан был?
Да, кристалл
как оптическая ось была вырезана по отношению к направлению распространения, если при одном проходе?
Насколько помню, под перпендикулярным углом вроде. Нет?
Okay. Probably other questions?
Вырезать кристалл под любым углом, ну, как известно, невозможно. Да? У вас какой-то был угол. Дальше вы его там можете поворачивать. Картинка, видимо, из...
Okay, I guess it's rather comment rather than question. Okay, so probably questions. So probably I will ask. Okay.
Что вырезает угол под углом, потом мы его определяем, то есть потом определяется оптимальный угол, под которым он вырезан. И дальше мы уже ищем нормаль, и от этого определяем, как преобразовывается излучение.
Я понимаю, но просто у меня вопрос очень конкретный был, все-таки не комментарий, а вопрос. Мы тоже работаем с этими кристаллами того же производителя, и меня просто интересует, какой конкретный кристалл, как он был вырезан. Они могут резать, там у них 2 ориентации, я это очень хорошо знаю. И вопрос очень конкретный, это не комментарий.
Значит, давайте я уточню и вам скажу.
Okay. Probably I will ask a question about the spectra in one pass and double pass geometry. This is probably one of the last slides. No.
Last slide.
Yeah, this one. So you mentioned that in this case you have additional lines. The spectrum becomes broader and you have additional lines. What's the microscopic origin of this drastic modification? Do you know why these lines appear here, emerge?
Not just.
What's the physics background?
I think this physics background is that we change the angle of SFG generation and more lines of в общем, начинает участвовать больше линий от изначального излучения, и из-за этого получается больше финальных линий. А тут, видимо, кристалл не так повернут, не под тем углом, и участвует изначально меньше излучения, то есть меньше спектра участвует, из этого меньше линий.
Спасибо.
Но это не те же, эти линии могут отличаться, если что, то есть это не те же линии, они могут не совпадать немного.
Спасибо, thank you. So, other questions? If it's not the case, let us thank the speaker and all speakers of this session. So our session is over, practically on time. And now I think that our schedule, у нас расписание какое-то сложное, да? Мы должны какое-то время, значит, не опоздать на автобус.
Thank you.